Hi, good morning, everyone. Can everybody hear me? Please let me know if you can hear me. All right, thank you so much. So, good morning and welcome to this workshop on blockchain and cybersecurity. My name is Hussein Akende Kadamasi, and I am the executive assistant at here at the African Blockchain Institute. So, the purpose of this workshop is to prepare you for like the upcoming hackathon. As you are all aware, you register for an hackathon program which is taking place on the 2nd of August. So this workshop is to prepare you for the upcoming hackathon. And the objective is to instill basic knowledge of blockchain and cybersecurity in the participants. So, like every other workshop, we expect you to take notes of important lessons, ask questions, and most importantly, pay attention to this workshop as this will be really helpful towards the hackathon program that is coming up. So I would also like to note that while we don't have, because of time, we don't have time to formally introduce ourselves individually. But as you move on, you introduce yourself. For example, if anybody wants to ask a question, you should introduce yourself first before asking a question or making any and giving any comment. So, and also would like to ask to switch on your cameras to set up the mode. Actually, let me get back. So I would ask to everybody to switch on their cameras so that we can see and understand who we are talking to. And also, if you have any questions, please be cordial and raise up your hand. Don't just unmute yourself and start speaking. You have to respect every other person that is here. So you raise up your hand and yes, I'll leave it to I'll leave it to Mrs. Olayinka Odeniran to give a keynote speech.
Thank you very much, Hassanat. Can you all hear me? All right, perfect. Well, good morning or good afternoon. It's early morning here. I am in the States, and I'm excited to talk to you guys about cybersecurity and blockchain. I have been in this industry for a while now. And, when cybersecurity first started, it wasn't something that everybody was willing to use. And people were confused about the word cybersecurity. What does it really mean? So, in my keynote today, I will talk about how cybersecurity and blockchain can basically integrate to build some really needed security measures that we currently need today in the world. My name is Olayinka Odeniran. I am the founder of CyberSec Watch, which is my cybersecurity company. I'm also the founder of Black Women Blockchain Council, which is an educational platform that teaches about blockchain. And through my experience, I've been able to merge the two. And I'll talk about a little bit about my background in this space as I go through my speech. So cybersecurity is a topic that has become increasingly important in our world. With the rise of cyber threats such as viruses, ransomware, and security breaches, it is more crucial than ever for businesses and individuals to take cybersecurity seriously. I've been in risk management for decades. My background stems from compliance and risk management before I jump into cybersecurity. Cybersecurity is not a new concept, and I don't mean that is just something that's has been growing over a few years, but it's been around for a long time. I can remember that in my years in compliance, we've always focused on components of cybersecurity. So it's no surprise that when regulations came and it was necessary for compliance to be involved in writing cybersecurity policies, that the regulators said, you know what, it's time. And so I took that as a call to action to go back to school and get my master's in cybersecurity policy and management. That was also around the time that I started jumping into blockchain. I immediately understood the need for security measures within blockchain, but many in the industry did not. And this was around 2015, 2016. I've always found that there was a way to integrate both of them. So today I want to talk to you about cybersecurity and how blockchain can be an enhancement to cybersecurity. While the interconnected world that we live in allows us to share and store information virtually, it brings enormous benefits. It also presents challenges and risks. Cybersecurity has never been as crucial as it is today. Traditional centralized systems have shown vulnerabilities. And now we have blockchain, a technology that holds great promise in revolutionizing our approach to cybersecurity. First, let's focus on the data integrity and immutability. How many times have we heard of situations where critical data was manipulated or even deleted, causing massive disruptions? With traditional centralized systems, this is a real threat, and it's a threat that we constantly face all across the globe. But blockchain technology brings a significant change. Blockchain is essentially digital blocks that contain records of transactions. Each block is connected to the other block, and the block before it and after it, making it difficult to tamper with a single record. Once a block is added to the chain, it is nearly impossible to change or delete it. The data becomes unimmutable part of the ledger. And this characteristic enhances the integrity of the stored information and drastically reduces the risk of data or fraud or even manipulation. However, maintaining data integrity is not the only advantage of using blockchain technology. One of the biggest pain points in cybersecurity is the vulnerability of centralized systems. Hackers often target decentralized systems because breaching a single point can potentially provide access to vast amounts of data. This is where blockchain distributed and decentralized nature comes into play. Data is not stored in a single location, but distributed across multiple nodes in the network. This decentralization means that even if a single node is compromised, the remaining nodes continue to function, ensuring that the system overall security. This makes the blockchain much more resilient to common attacks and provides a more robust platform for secure transaction. Moving on to a feature that truly sets blockchain apart from all other technology is the advanced cryptography. In the realm of cybersecurity, encryption is our best friend, right? Blockchain employs cryptographic algorithms that currently are beyond the reach of even the most powerful computers nowadays. Blockchain networks blockchain uses public and private keys, long strings of numbers and letters for transactions. This level of encryption provides an added layer of protection against cyber threats. The private key is like a digital signature. Without it, transactions cannot be authorized. This makes it incredibly secure and near impossible to crack. Now, let's talk about transparency. Another hallmark feature of blockchain. In most cases, all transactions and their details are visible to everyone on the network. This level of transparency provides an audible trail of all transactions that have been occurred on the network, which makes it easier to detect, counteract suspicious activities, which is very important in cybersecurity. Moreover, when integrated with artificial intelligence or machine learning systems, the blockchain becomes a potent tool for detecting, mitigating cyber threats. It becomes possible to predict patterns, recognize irregularities, and respond to threats that are more effectively. When we have smart contracts are self-executing contracts with the terms of the agreement directly written into the code. They execute transactions automatically once the predefined conditions are met. These smart contracts operate on the blockchain, which means that they are secure as the transactions on the network. They help maintain privacy, confidentiality, and reduces the need for intermediaries and minimizes the risk of fraud. We cannot overlook the resilience of blockchain technology against distributed denial of service, or DDoS attacks. Such attacks aim to overwhelm the network with excessive traffic, causing services to become unavailable. However, thanks to blockchain decentralized nature, the impact of such attacks can be mitigated, as there is only one single point of failure, and that single point of failure does not impact the rest of the network. Last but not least, let's touch on the secure communication. Blockchain can be used to establish secure communication channels, proving particularly useful in the field of messaging and communications. For instance, blockchain-based domain name system solutions are emerging as secure alternatives to the traditional DNS, reducing the risk of DNS-based attacks. There is so much that could be done with blockchain. By integrating blockchain technology into cybersecurity strategies, we can significantly enhance our defenses against cyber threats. Its unique characteristics, of course, the decentralization, immutability, and the advanced cryptography makes it a powerful tool in our arsenal tool. However, let us remember that blockchain is not a silver bullet for all security issues. It is an additional layer that we can use to defend complete traditional cybersecurity measures. As we forge ahead, it is exciting for our digital future to be able to integrate the two. So let us continue to explore, develop, and integrate robust technologies like blockchain to help fortify the defenses and create a safer and more secure digital world for ourselves. I want to thank you all and good luck on the hackathon.
Thank you so much for that. That was truly insightful. Okay, so I'll leave it to the team to move on with the
What did you say, Hussein?
Yes, I said we'll leave it to teams to delve into the curriculum for this workshop. Thanks.
Hello, guys.
Yes, good morning.
Okay, so can we start the presentation?
Yes, please. You can go on with the presentation.
Okay, perfect. I will be sharing my screen, then I will be introducing what we'll be doing today and what we will be covering about blockchain and the content of the training. So can you guys see my screen?
Yes.
Okay, perfect. So hello everyone. I hope you are all doing well. So today's training will be about blockchain as a technology. We will be introducing the blockchain technology, smart contracts, and we will be covering the cybersecurity aspect of this technology. So first, I will be introducing myself. I am Farouk Al-Alem. I am a lead blockchain auditor at Shellboxes. So Shellboxes is a development and audit firm, which is mainly specialized in the blockchain technology. We have been in the field for many years, and we've worked with many promising projects in the blockchain space for both the development phase and also the auditing phase, and assuring that all the protocol are secure. So I have over 2 years of experience in smart contract auditing. So we've delivered many auditing reports to clients, and we have discovered multiple critical and high vulnerabilities in several protocols, which help us to secure a great amount of funds that could have been lost if those bugs were exploited. So I'm happy to be here, happy to be performing this presentation, and I hope it will be instructive and also interactive. So if you have any trouble understanding anything, or if you have any question, feel free to unmute your mic and drop your question. I will be happy to answer and discuss the answer. So in order for the course to be as instructive as possible and as interactive as possible, you can ask questions at any time. So in this presentation, we will be following this outline. So we'll be mainly covering four axes, which are introducing the blockchain technology, how it works from a high level, how the consensus works, what are the cryptographic mechanisms that makes it immutable and also secure. And we will be also covering the smart contracts, what are smart contracts, and also how can we make smart contracts secure, in addition to a roadmap for anyone attending the course, if anyone wants to become a blockchain developer or a smart contract auditor. We will be presenting, or will be given a roadmap with the steps or the milestones that you'll need to achieve in order to reach your objective. So when it comes to the blockchain introduction, we will be covering the main difference between the client-server architecture and the peer-to-peer model. Then we'll be covering the cryptographic basics of the blockchain, what are hashing algorithms, signature algorithms, etc. We will be introducing the Byzantine general problem, which is the main problem that we are trying to solve in the blockchain, and how the Satoshi Nakamoto paper helped us to solve this problem. We will be focusing on how data is stored in the blockchain and different models of storage, and we will be introducing smart contracts. Then when it comes to development, we will be talking about the Ethereum virtual machine, which is basically the environment where smart contracts are executed. We will be covering Solidity, which is the most famous or the most used programming language in Ethereum and other EVM-based blockchains. We will be also covering development frameworks, what frameworks are commonly used in the field, and how those frameworks help us to develop secure smart contracts. And we'll be covering how to deploy smart contracts and how to test them, test the functionalities and the correctness of the code. Then we'll be covering the security part of smart contracts. What are the common vulnerabilities that exist? how can we spot those vulnerabilities. We'll be talking about smart contract auditing and how is it helpful, and we'll also be covering how to write proof of concepts when it comes to found vulnerabilities. Then we'll be talking about the roadmaps of how to be a blockchain developer and blockchain or smart contract cybersecurity auditor. So first, let's introduce the blockchain technology. So the first thing that we'll be talking about is the architecture. So we have a difference between the client server and the peer-to-peer model. So we're always used to use the client server architecture, which basically what made the internet possible. So the architecture is simple. We have multiple type of clients. We have laptops, computers, mobile phones, which can connect to the internet, which is basically the biggest network that we can communicate in. And all those clients, for any service that you want, you can reach out to a specific centralized server. So for example, if I want to find some information, I will be talking to the server of a search engine, for example Google or Bing, and I will be communicating to this specific server in order to get my information. So this is a request from me, and then the server will provide me with a response that will help me get the information that I want. And the same can be applied for any type of services. So this is the client server architecture. This is how it works. It offers us a lot of advantages, which is scalability. Also, it's kind of simple to implement. So it's fast. It's also fast. So we have one specific server. We talk about it. We send a request and we get the response. But it has a lot of advantages, but also it has a lot of drawbacks. The first one is centralization. So if this server falls down, we'll have denial of service. If the owner of the server decides to act malicious, then we'll be all at risk. For example, if I search specific information, it might give me a false information about the specific thing that I am asking about. And for example, if the server got hacked, we have no way to prevent that. So there can be a lot of issues concerning this architecture. So the second architecture that we have is the peer-to-peer model, where we have many computers, or as we say, many nodes that are talking to each other. So these nodes provide services to each other. So the data is stored everywhere. Any node can communicate with another node, and we basically have a decentralized architecture, which has multiple advantages. So if one of the nodes, or even two or three of the nodes, get compromised, we will have a lot of nodes that can cover the service. So the service will not have a denial of service. And also, if someone wants to act malicious, we can achieve consensus using multiple techniques that will allow us to figure out who is acting malicious and what's the right action to do. So we can see that every architecture have its advantages and disadvantages. So the main we can never say that this architecture is the best, or the other one is the best. So definitely there are advantages and disadvantages for each one, and the choice of architecture will really depends on the use case. So for some use cases, the client server architecture is preferred, but in some other services, the peer-to-peer is the kind of the most optimal solution. So before talking about the blockchain itself, let's first talk about some cryptography basics. So cryptography is the main aspects that, or the main the main thing that made the blockchain technology possible. So without cryptography, almost all the functionalities of the blockchain cannot be achieved. So the cryptography is the main mechanism that we rely on in blockchain. So to avoid trusting a specific party or a centralized party, we mainly rely on mathematics and the cryptography or the cryptology science in order for us to make things secure. So the first thing that we will cover is hashing functions. So a hashing function is a one-way function which help us to move on from a plain text to a hash text. So we can consider the hash text as some kind of fingerprint or a specific string that can basically identify the plain text, and it has a lot of security. What was that? Is someone asking a question or? I cannot really hear what's being said.
Mute them. Mute them. They are speaking other things.
Okay. Okay, so I guess we can continue. So as I said, hashing functions has a lot of specific things that are related to them. So the first thing is hashing functions are irreversible. So if we have a hash text, we cannot reverse it in order to get to the plain text. So there is no direct method. The only method that can be done is brute force, which can be really computationally intensive. It's almost impossible to achieve that. So the main functionality about hashing algorithms is it's one-way function, and it cannot be reversed. Also, most of the hashing functions are basically prevent collisions. So if we have a plain text, we will have a hash to it. So if we hash a plain text as much as we want, we will basically get in the same hash. So it's basically deterministic. So if we hash the same text using the same function, we will always be getting deterministic output. And also this output has a specific length. So for example, for a specific algorithm, we will have always 20 bytes, no matter how much content exists in the plain text. Or we can even hash images and files and even gigabyte of files, and we will always be getting a length that is limited. So I will be sharing a diagram in order to make it more clear before we move on to the next thing. So let me share my screen again. Can you guys see my screen?
Yes.
Okay, perfect. So this is a simplistic example of how hash functions work. We basically provide it with any content that we want. So and as an input, and it provides us with the hash, which is a content that is limited in size. So if we have small word, we will always be getting this size. And if we have a long text, so no matter how high it is, the hash changes from changing the text, and we will always be getting the same output. And if you give me this exact string, I cannot get back to the text that was given before. So this is an important mechanism of hashing functions, and we'll be talking about how can those be used in the blockchain technology. So, and if we change only one character, so if I add, for example, just one here, it will change the whole hash. So if we add and remove it, we will notice that it's not just one character or a little change in the hash completely changes. So if I know the hash of test one, and I want to discover the hashes will be too much different. Is the hashing functions clear? Do you have any questions, guys?
Very clear for me.
Okay, perfect. So now we'll be moving on to the next one. So yeah, the second thing is encryption. So we have different kind of encryptions. We can basically divide them into two main areas, which are symmetric encryption and asymmetric encryption. So there is one main difference between the two. So in the symmetric encryption, we have a method that we have basically a key, a secret key that should be shared between the two parties that want to assure confidentiality. So the main can you guys unmute? So the main functionality that we are getting with encryption is confidentiality. So if we have an insecure channel of communication between two entities, basically we will need to assure confidentiality. And we can even communicate in a channel that is insecure, that is transparent, and anyone can see it, and still assure confidentiality due to encryption. So we basically have a plain text that we want to communicate to another party without anyone else knowing about it. So we will need to have a secret key that is shared between the two entities. We encrypt this. There is some noise in the background, so if kind of hard to talk. There is a lot of noise in the background. Okay. So as I said, we can communicate into a channel that is insecure and still assure confidentiality due to encryption. So we basically have a shared key between us and the party that we want to communicate with. We have a plain text. We encrypt it using a specific encryption function that takes in the output the plain text that we want to encrypt and also the secret key. And it gives us a ciphertext that cannot be understood by anyone except the other party that has the same secret key. So you can even know the function that I used in order to encrypt, but if you do not have the secret key, you cannot manage to get this or to discover the plain text that was used in order to produce the ciphertext. So, and if the other party receives the ciphertext, basically he uses a decryption function, and he gives it the same secret key as an input in order to get back the plain text. So this is a simple method. There are a lot of encryption functions, or specifically symmetric encryption functions that are used. The most standard one is AES. So it is the mostly used encryption or type of encryption in the real application world. So the second type is asymmetric encryption, which is kind of different. So in this specific type of encryption, we do not have a common or one key that is shared between us and the party, as it is kind of hard to exchange keys. So the main drawback of symmetric encryption is the fact that we need to share a secret key between us and the party, and we already have an insecure channel, so we cannot transmit the secret key in the network or in this specific insecure channel. So in order to solve that, basically everyone has a pair of keys. So basically two keys. We have a public key and a private key for each specific party. The public key is something that can be known for everyone. It can even be used as an identifier. So I have a public key. Everyone can know that Farouk's public key is this specific key, and anyone can discover the key of any specific party, and there are no security sacrifices in that. So everyone can know the public key of each other. But we have also a private key that should be secured and that should never be shared with anyone. So it's basically a key that needs to be known by only the key holder. So we do not, even the party that we want to communicate with does not need to know the private key, and that's where the beauty of asymmetric encryption comes from. So we have two keys, public key and private key, and we use those in order to achieve our objective, which is communicating over an insecure channel and still assuring confidentiality and the fact that no one can know what the plain text that we want to share is. So how it works, basically we use if I want to communicate with a specific person called Alice, for example, I grab the public key of Alice. So I take this key and I use it to encrypt the ciphertext. So now that we have a ciphertext, the only one that can decrypt the ciphertext is the owner of the private key that is associated with the public key that was used in encryption. So if I encrypt the message using the public key of Alice, only the private key of Alice can decrypt this message. So you cannot use the same mechanism that we talked about in symmetric encryption and use the same key that was used in encryption to decrypt the message. So if you use the public key of Alice to decrypt the message, you will not be getting the text that you want. So if we encrypt with the public key of specific party, only the private key of this specific party is able to decrypt the message. That's why we need to keep our private key always secure, and no one should know about it. Is everything clear when it comes to the symmetric encryption and the asymmetric encryption and the differences between those? Do you guys have any questions? Okay, so if there are no questions for now, we can, I guess we can move on to the next part. So, the next cryptographic mechanism that we will be covering is digital signatures. So digital signatures is a powerful technology in cryptography. That's one of the main mechanisms that we rely on in blockchain. And yeah, it is basically digital signatures. It's a way for us in order to get authenticity. So we talked before about hashing functions. Hashing functions are mainly used for integrity. So if you want to know if the message was not changed, we get the message and its hash, and if the output that we are getting, we can hash it again. If the hash is different, we can deduce that the data was manipulated. So hashing functions provide us with integrity. When it comes to encryption, as we said, it provides us with confidentiality. So confidentiality is the ability for us to work in an insecure environment or a public channel and still assure confidentiality, and that no one can read anything except for the parties that are allowed to do so. So yeah, and then we can we can move on to the digital signatures, which provide us with authenticity. So encryption and hashing, etc., can still be manipulated. So for example, if I send a message to Alice, she can decrypt the message, etc., in a confidential way, but she cannot know that I am the one who sent the message. So we do not have authenticity. So digital signatures is what assures that if Alice receives my message, she can know that I am the one who provided her this specific message. And this is a very powerful mechanism that basically made the blockchain possible. So here in this situation, we have a sender and receiver. So there are a lot of ways or a lot of digital signature schemes. So it depends on the encryption algorithm that we are using and the type of private keys and public keys that are used. So the sender basically have a specific message. First, he sends the message to the receiver, and also then he hashes the message. Then he gets the message digest, which is basically the signature, and which is basically the hash, and then he encrypts the message using his private key. So after that, he gets basically a signed digest, and since the receiver already knows the public key of the sender, he can then use this public key in order to decrypt this message. And if he finds that there is the same hash that was provided before, he can deduce that this sender, or the one who is associated with the public key that was used in decryption, is actually the one who sends the message. So this is a very powerful way in order to get authenticity and to make sure that the message that we have received is was sent before by this specific party, or the person that we are waiting for it to send the message. Is everything clear when it comes to digital signatures? And as I said, in digital signatures, there are a lot of approaches. So there is no one specific standard that everyone follows. It really depends on the encryption algorithm that we are using. So, for example, in RSA, we can use this specific method, where if we are using elliptic curves as an encryption algorithm, we can use ECGSA. So it really depends on the algorithms we are using. But the general idea about digital signatures is that we can verify the authenticity of a message and who sent this message. So I guess for now there are no questions. Feel free to unmute or use the chat to ask any questions if you have. So now we can move on to the Byzantine general problem, which is the main problem that we are trying to solve in blockchain. So as we talked about before, there are a lot of drawbacks when using a client server architecture. There is a lot of centralization, and if we want or our values mainly align with decentralization, we will be needing to use a peer-to-peer model where we have many nodes that are communicating with each other. But also those nodes cannot be trusted. So we need to have a mechanism in order for us to basically coordinate and basically detect if there is someone that is acting malicious or is trying to provide us with false information, etc. So the Byzantine general problem is a known problem, and it's basically a situation that shows us that in order to use the peer-to-peer model, we need a lot of mechanisms in order to achieve what we call consensus, or for us or for many nodes to agree on the same thing. So we have many nodes that can act however they want, but we need a mechanism in order to coordinate and to get the same answer, and hopefully this answer can be the correct one. So the Byzantine general problem is presented in the image. So we basically, in this example, we have 7 generals which are trying to perform an attack over a city that they want. So here we have a war situation. We have 7 generals that cannot communicate with each other. So everyone is independent. So that's an example that is aligned with the peer-to-peer architecture that we talked about before. So if the generals arrive to coordinate an attack in order to attack the city or a specific attack, this will lead them to victory. So the objective is for the 7 generals to achieve consensus and to agree on the same thing, and they can all execute this specific instruction. So if for example they receive a false message from inside the city and they trust this message, it can be an attacker or it can be someone that is acting malicious. So we will have, for example, 2 people that are backing off and 3 people that are attacking this city, and the other 2 are waiting. So we will have uncoordination problems, which will lead us to basically losing the war. So that's basically a method to illustrate the problem that we will be having in a peer-to-peer architecture. So for example, if I say that a person, or for example, let's take Alice as an example once again. If Alice is saying something, how can I verify that she's saying the right thing? So we will need a consensus mechanism or a specific mechanism in order for us to basically to get to the right answer and we can all agree on. So we need to have coordination. Is there any question? So Jacob is saying, I have a question on digital signatures. Does digital signatures have to be specific format like human readable form, or any message shared following such encryption process can be considered as digital signature? So digital signatures are basically unreadable text. So if you want, I can share an example of digital signature in order to make it more clear. So just 1 second. Okay, so I will be sharing the screen once again. So I will be explaining this specific diagram in order to make the signatures or this digital signatures aspect more clear. So basically the first thing that we will be looking at is the key pair. So the key, can you see my mouse? Hello?
I can see it.
Okay. So the first thing that we have is a key pair, as we talked about. So everyone has a private key and a public key. Here we have a scheme that represents how digital signatures work. So basically, I have a specific text. So we will basically ignore encryption and also confidentiality. So the only thing that we are trying to assure here is the fact that the message is authentic. So the first thing that we use is a sign-in function or a sign-in algorithm that takes the private key as an input and also the message that we want to sign. Then, as an output, we can extract the signature, which looks like that. So the signature is like that. So, for example, if we specify this message, we will be getting a specific signature. If I change the message, for example, if I add 111, I will be changing the signature. So basically, this signature function takes a plain text which is human readable, and it gives us with a specific string that's not necessarily human readable, but it can be used in order to prove authenticity. So for example, if I want to communicate with Alice, I will give it and to prove to her that I am indeed Farouk. So I provide her with this signature, with this signed message, and then she can use this signed message in order to recover the address that has signed the message before. So the only thing that she needs is to have the initial message and also the signature. And this recover method, or the recover, it's kind of similar to the decryption method. So in order for, in the context of confidentiality, we encrypt and we decrypt the message. In the context of signatures, we have the sign-in process, and the opposite process is recovering. So the sign-in process is producing the signed message, and the recovering is from the message and the signature, getting who signed the message. So the recovery message is the method that we can use in order to see who signed this message. So we give it the message and the signature, and it provides us with the address of who signed the message. So in this key pair, the address who signed the message is this one here, is the one that is covered here. And when we sign the message, Alice gets the message, and when we recover the message, we get the address here. So as we can notice, the address is the same. So Alice was able to assure that the message was actually signed by this specific address. So here, that's how we can prove authenticity. Is it clear for the one who asked for Jabo? Feel free to let me know if you need any further explanations.
May I ask?
Yeah, sure.
I didn't understood well about those chats. Maybe you can repeat in summary, if possible.
Can you please repeat? I didn't hear you well.
We didn't understood that chats over here. Maybe you can repeat summary, if it is possible.
This diagram?
Yes.
Yeah, sure.
Summary. Yeah.
Yeah, okay. So let's not focus on everything. So let's take it part by part. So the first thing that we need in order to perform this operation is a specific key pair. So imagine all the attendants here in the meeting now. So everyone have a specific key pair, which is basically a private key that's only known by the specific person that owns it. So I have my private key that no one else should know, and everyone else has his own private key that he should make secure. And also every one of us has a public key which can be known by everyone, and it will not cause us any security vulnerabilities. So the first thing that we need is a key pair. So in order for us to send a signed message, so for example, if I want to say that this course is about blockchain, so I have this message, and we have an insecure channel. So everyone here in the meeting can be a malicious person and can probably say a message on behalf of me. So I am the presenter, and he will just say to you that this course, for example, is not about blockchain. So how can you trust that a specific message was provided by a specific person? So this is where digital signatures comes handy. So if I want, for example, I am the presenter. If I want to say that this course is about blockchain, I have to provide you a signed message, not just a message. So this course is about blockchain is a message that can be produced by any one of you. Anyone can say it, and we have no mechanism in order for us to know that the presenter is the one who said it. So in order for me to convince you that I am the presenter and I am the one who said that this course is about blockchain, first the address is something that's extractable from the public key. So everyone here knows the public key of the presenter. So that should be known by everyone. So in order for me to convince you, I have to provide you with the signed message. How can I do it? I choose a signature function, which I provided with the message and my own private key. So this signature function is used to provide a signed message. So I give it that this course is about blockchain, and I also give it my private key, which cannot be given by anyone. So only me, the owner of the private key, will be able to provide it with this specific private key. So I give it the message and the private key, and it gives me an output that like that as a string, which is basically a signed message. So if I want to send you now the message, I will send you that the course is about blockchain, and here is my signature, which proves that I am the presenter, that I am the owner of this address, and actually I am the one who said that this course is about blockchain. So in order for you to verify that and verify that I am saying the truth, you do not have to trust me personally, but you have to trust the mathematics of the decryption or the signature method. So you will use a recover function. You will give it the message. You will give it, this course is about blockchain, and you will give it the signature, and the recover method will give you based on the message and on the signature who signed this message, and then you will be getting this output, which is the address of the signer, and you compare it with the address of the person that you want to know. So if for example, you know that I am the presenter and my address starts with is this following, which we start with 0x7a. If you use the recover method and you get the same address, you will be sure that mathematically that Farouk, the presenter, is actually the one who signed this message, is actually the one who said that this course is about blockchain. If you get a different address, you will directly conclude that this message was not signed by the presenter, and it is another person that's trying to give you a message that is not authentic. So this is basically how it works. It is basically used to prove that a specific message was signed by a specific entity or by a specific key pair. Is it clear for now? Okay, I guess.
It's clear. Thank you, sir.
Yeah, perfect. So feel free to let me know if you have any questions. So I guess now we can move on to the next part. So I will be going back to the slides. So as we said, the Byzantine general problem is a problem that's concerning coordination. So when we are using a peer-to-peer model, we have many nodes. Anyone can act malicious, and we basically need a mechanism to ensure that we are doing the right thing, which can be complicated. So there are a lot of ways to go with that, but the first solution, or the first concrete solution that was provided in order to solve this problem is proof of work. So proof of work is a consensus mechanism that's basically used to solve the Byzantine general problem and to assure consensus and coordination between multiple nodes that can act however they want, and we can still do the right thing based on many nodes acting in the network.
So proof of work is a concept that was introduced in 2008 by a white paper that's produced by an anonymous person, which is Satoshi Nakamoto. And this is actually the white paper of Bitcoin, which is the first application of blockchain or the first real world application of blockchain. And yeah, this is basically the first thing that was provided in the white paper. So he called it Bitcoin, and he is saying that it's a peer-to-peer electronic cash system. So it's a peer-to-peer architecture where we can exchange cash. So the main mechanism that everyone relied on before in order to exchange cash is banking systems. So banking is a centralized party. So for example, if I want to send for example $100 to Alice, I will reach out to my bank, and I will give them the account number of Alice, and they will I will be sending them the money, and they will be sending this money to Alice. So here we are basically acting just like the client server model. So I give my request to a specific centralized party, and this centralized party gives me the service and provides Alice with the money that I gave them. So we are mainly relying on a third party to execute this. But when it comes to Bitcoin, we are not relying on any centralized party. We are basically relying on the mathematics and the cryptographic mechanisms that have been mathematically proven to be secure in order for us to basically introduce a trust mechanism in a trustless system. So in a system where we have multiple nodes that can act however they want, they can act malicious, they can act basically correct, we can still assure security, and we can still assure that everyone, or at least the consensus or the popular opinion, is the correct one. So this was introduced in the Bitcoin white paper in 2008 by Satoshi Nakamoto, which is an anonymous person, and until now no one still knows that who is the real person that's behind Bitcoin, which is under the name of Satoshi Nakamoto. So he basically introduced mechanisms in order to have trust in a trustless system, which is a peer-to-peer network. So the main mechanism that he introduced, so he had introduced a lot of aspects. The main mechanism that given is the concept of blockchain and the concept of proof of work, which is the consensus mechanism that we are relying on to have a trust in a peer-to-peer network. So he basically said that anyone can, of course, in a peer-to-peer model, anyone can broadcast a message to anyone else, and anyone can read it. So, for example, if Alice says that, for example, I sent 100 bitcoins to Farouk, how can we assure that she actually does that, and how can we assure that she actually owns 100 bitcoins? So he introduced first a concept where we have transactions. Transactions are basically a transmission in the context of Bitcoin. It is limited to financial transactions. So financial transaction is the fact that I can say that I sent 100 or 10 bitcoins to Alice. Alice can say that she sent 50 bitcoin to Bob, etc. So everyone can broadcast some message like that. But how can we prove that this message is the correct one? So in order first to prove that, for example, I said the message, we rely on the digital signatures that was introduced before. So if I want to say that I sent 10 bitcoins to Alice, I also need to provide a signature, so everyone can verify the signature and know that it's actually me who said that. So this is very important, as if we remove the digital signature, anyone can see that Farouk sent 10 bitcoins to Alice, and no one can verify if that's a true statement that was produced by me or by a malicious party or an attacker inside the network. So digital signatures are an important aspects of the blockchain technology overall. So, and these transactions, Satoshi Nakamoto proposed to gather those transactions in specific blocks. So if I say that I sent 10 bitcoins to a specific person, that person sent 50 bitcoins to another person, etc. We basically, everyone broadcasts his transaction along with the signed message, and we basically produce a block of transactions. Then we verify all of them at once. So we verify the signatures of each transaction, and we also verify the statement and if it's true or not. So, for example, if I have zero Bitcoin in my balance, I cannot send Bitcoin. So that I first have to receive Bitcoin from someone else. That way I can send it. It's like working with dollars. So if I have $0, I cannot send you $1 million. So we have to assure that everyone has a specific balance, and everyone cannot send more than the balance that he has. So we cannot be producing, or basically it's just like printing money or fake money. So that's the main thing. The first thing is proving authenticity. So the message have to be authentic. We have to verify who sent the message, and then we should verify that the sender of the message have the required balance in order to perform this transaction. So after getting this block, we basically verify it and we hash it. And we basically try to solve a mathematical problem. So in order for us or in order for the network to trust us, so for each block we select a person who is called the miner. So a miner basically is a person in charge who everyone can propose to be a miner. A miner is a specific party that basically each block we allocate a specific miner. So we cannot have all the blocks are being mined by one specific miner. It will be insecure and it will not be decentralized. Actually, it will be just like a centralized system where one person or one entity is controlling the system. So for each specific block of transactions, we select a miner. So how can we select the miner? Can you please repeat? Is that a question? I didn't hear it well.
Not a question.
Okay. So yeah, as I was saying, basically, in order for you to be a miner, you have to solve a mathematical problem. What is this mathematical problem? Is you will have to find a specific number that will achieve a specific condition. So let me get back to the hashing functions in order to tell you how this works exactly. Okay, so let's suppose, for example, that we have a specific message like that. Okay. So, for example, just for simplicity, I will say that Farouk sent 10 BTC to Alice, and Alice sent I don't know, 5 BTC to Bob. So for sake of simplicity, let's say we have 2 transactions. And also for simplicity, let's say that we verified the signature. So we know that actually Farouk is the one who said that he wanted to transfer 10 BTC to Alice, and Alice actually said that she sent 5 BTC to Bob. So let's assume that we verified the signatures. So we have already authenticity. So basically, the mathematical problem that you have to solve in order to be a miner is basically, let's say we have a number here, and this number is called the nonce. It can be any integer value. So it can be 0, it can be 1, it can be 2. So as you can see, if we change this number, we change the hash. So we will be always getting a different hash. So the challenge for you is to get a hash that starts by, for example, let's say an easy one, which is 1 0. So it should be 0x0, and then you will have some random characters. So the thing that the miner does is he basically brute forces over the nonces in order to have a hash that starts with 0. So let's say I send 0, so we have 0x3, which is not valid. Let's start by 1, and here I solved the problem. I got a hash that starts by 1 0. So in order to make the problem more complex, I can say that you have to find a hash that starts with 0x00, then random characters. So it will be harder for me to find. So I try 2, I try 3, I try 4, I try 5, I try 6, etc. And I will be basically brute forcing in order to get to the output that is required. Can you please unmute for those that have no questions for now? So Akimana,
nizo ndi gukoresha byanze we.
for the host, can you please unmute the mic?
You can mute her.
naona gahutoro uja jena bari kujyayo bayimaye ntabyo nari nzi byarabateye okay sisi unite
The host can mute her.
bashaka bakambare this is a million good.
Cynthia, you meet your
Okay, so I guess we can now continue. So as I said before, basically the problem or the mathematical problem that you have to solve is a brute force problem, which you will be basically trying over multiple nonce numbers, just brute forcing one by one in order to get a hash that starts by a specific number of zeros. So when I said it starts with 1 0 or 2 zeros, it is not a fixed number. It depends on the network and the load that and the traffic of the network. So if I said that starts with 1 0, that's an easy problem. With 2 zeros, it's a harder problem. And if I add more zeros that are required, it will be even harder to find the hash. So that's why the popular opinion of mining is that you require very big hardware, very powerful graphic cards in order to be a miner. So you will have basically to solve a complex problem that requires a lot of computation work. So I will be getting back to the slides. So yeah, that's how it works. So you basically hash all the transactions in addition to the hash of the previous block. So in order for me to produce the block n, I should have the content of the block n and also the hash of the previous block that was mined by another miner, and I should hash those together, add the nonce variable and brute force over it in order to get the number of zeros that are required. So here we have, for example, 10 zeros to 20 zeros. It really depends on the required complexity for the network and the specific case. So yeah, that's basically it. So in order for you to be selected as a miner and that we can trust you, you have to solve a specific mathematical problem. So you will be losing a lot of energy, and you will be investing in hardware and graphic cards that should be powerful in order for you to be a miner. So if we talk about game theory, so the only incentive that you will be the only way you can be solving this problem is that you are incentivized to do it. So in order for you to be a miner, you will basically need to solve this problem, and you will be investing a lot of money in order to do it. So you should be expecting a reward. So all the miners basically get a reward from producing a specific block. So that's why mining, that's why how we incentivize people to be miners or to secure our network. We basically give them a reward, and the reward can be got by different mechanisms. So for Bitcoin, we basically like printing money. We basically provide them with newly minted money, and for Ethereum, for example, there are gas fees. So anyone that wants to execute transactions, he needs to pay a small fee, and these fees that are paid by the users or the persons who perform transactions are gathered and are given to the miner who solves the problem. So this is overall how proof of work works. Do you guys have any questions about that? Okay, I guess if there are no questions, we can move on to the next one. Guys, okay. So proof of work is very good. Proof of work offers us a lot of security, but proof of work has some disadvantages. The main one, which is energy consumption. So in order for people to solve these problems, as I said, they will need to invest a lot of hardware and powerful CPUs, powerful GPUs, and in order for those to work, they need electricity. So and powerful graphic cards consume a lot of electricity. So if we have a lot of miners all over the world, basically we will be losing a lot of energy that's used by every miner. This is helping us to secure the network, but it's kind of energy consuming. So that's where proof of stake was introduced. So proof of work is basically trying or having a miner that is trying to solve a problem or invest a lot of hardware and a lot of energy in order to solve a problem to basically validate transactions. And proof of stake is different. Proof of stake is basically for me to be a miner, I have to stake for example 10 Bitcoin, for example. Bitcoin, by the way, still uses proof of work, and there are a lot of blockchains that use proof of work and other ones that use proof of stake. For example, Ethereum, which is the famous one, uses before used proof of stake, but recently they have merged or they have moved into using proof of stake. So for example, if I am a validator in Ethereum, in order for me to produce a block, I have basically I do not have to solve a mathematical problem, but I have to provide a staked ether. So I have to provide a big amount of the Ethereum coin, basically as a guarantee. So this, if I give the protocol, then for example, the minimum for you to stake is 30 Ethereum. So if I stake my money, if I stake 32 Ethereum, I will have the chance to be a validator. So basically, with this money that I invest is basically locked. And after I validate the block, and after other people verify that I validated the block correctly, then I can receive back my guarantee or my stake. So the amount of money that I give to the protocol and that is locked is called stake. So basically, we are staking a specific amount of Ethereum. And if I try, for example, to be malicious, to be an attacker, for example, to see that someone produced a specific transaction and he did not actually produce it, if I try to be an attacker and I get detected by other nodes, which is completely easy, my stake will be lost. So, and the stake has a big value that helps us secure the network. So is proof of stake clear?
I have a question.
Yeah, sure.
All right. Anyway, you said like proof of stake, we need to stake like amount of token,
Yeah.
so that we can be a validator, and the validation needs a nonce. Okay.
Yeah.
So, and that nonce to be there, we need computational power and even energy power. Okay.
Yeah.
So which computer or which node we engage in this activity so that we can have that nonce to validate that transaction. Or for proof of work, it's clear that if you are able to do those calculations or to use your GPU to have that nonce, then you will be validating. But it's not clear, like on proof of stake, which computer or which node will be doing this calculation. Okay.
Yeah, very good question. So in proof of stake, we do not have a computational problem. So in proof of stake, you just hash the previous the content of the new block and the hash of the previous block in order to keep the chain, and you just hash that. If you get selected as a validator, you get to do that and you get to produce the block. So there is no computation problem, there are no GPUs, etc. So that's the advantage of proof of stake. We do not have a computational problem, which helps us to reduce the energy consumption. So we are basically in proof of work, we are relying on a person to allocate a lot of computation and the energy to solve the mathematical problem. That's how we can trust this person. But in proof of stake, we do not have a computational problem. We have many people that are staking a high amount of funds or of money. And we are basically relying on the fact that if they act malicious and we detect them, we basically get their money. So if, for example, I invest 32 Ether, this is a huge amount of money. and basically it's very very requiring. And if I ever get caught attacking the network or trying to produce a false information, I will not be getting my money back. So it is basically, we are relying on the fact that they are staking some money as a guarantee. If they get caught trying to produce false information, we can get their money. So that's how we can trust that the miners will not act malicious most of the time. So if a miner gets caught one time, they will be in proof of stake, we call that slashing. So every validator or miner that is in the network acting malicious can be slashed, and his stake can be lost. Is that clear?
Yes, it is clear. So the miner in proof of stake, they get their money back with the rewards,
Yeah.
but later after the validation of the block.
Yes, after we have what we call block finality, when we are sure that the block is correctly produced.
Okay.
Perfect. Does anyone else have any questions? Okay, so is there a question in chat? Okay. So yeah, I guess we can move on to the next part. The next part is about what we call the blockchain trilemma. So this problem is a known problem concerning the blockchain, and we basically have a trilemma of three aspects, which are decentralization, security, and scalability. So the problem states that we can only. Can you guys unmute? There is some noise in the background.
Yes, we can.
Hi. Is it okay if I say something or suggest? Is that okay?
I do not hear you well.
So I'm saying, is it okay if I suggest something real quick? Because we've been learning for a while now, and I think like everybody should just take 5 minutes to relax and digest before we go back into the
Yeah, sure. So we take a 5-minute break.
yes.
Yeah, okay, sure.
Okay, so we'll be back here by 11:35. Like we'll start the class again by 11:30. So drink water or whatever that you want to do. Thank you.
Okay.
Is being recorded.
Bro, Mugisha waramutse.
All right, everybody.
Mwaramutse neza.
Time to
Ni Joshua, bino bintu uri kubyumva?
Turavuganira muri group.
Nta kibazo.
Yeah.
Okay, it's time for the workshop to commence. Thank you.
Hello, guys. Can we continue?
Yes, we can. Yes.
Sure.
So we can continue.
So first, before continuing, do you guys have any questions, anything that is unclear, either about cryptography, proof of work, proof of stake, before we can move on to the next thing?
I have some question.
Sure. What's your question?
I have question about proof of work. I didn't understood well if the criteria the miner used to solve that problems.
What exact criteria? So, as I said before, the miner just brute forces a specific nonce in order to get a specific hash that starts with a number of a specific number of zeros. So he basically solving a computational problem. Can you please be more specific in the question?
Yeah, just I was thinking if the miner use his specific knowledge he have about solving that question or the criteria used to solve that complex questions. Yeah, he solves.
No, there are no like mathematical equations, etc. So it's basically a hash function that's used on the new content of the block, and also we hash the previous hash of the block. So in order for us to have a chain of blocks, that's what we call why we call it a blockchain. And he basically, as I demonstrated before, let me show that again. So as you can see in my screen, he basically keep on trying different numbers. So I can try this number, or I can try this number, etc. So he basically changes the nonce in order for him to produce a hash or a final hash of the block that starts with a specific number of zeros. So that's the mathematical problem that he is trying to solve. And everyone can verify that he solved this mathematical problem. So in order for him to produce the block, he needs to find the nonce. He will sacrifice a lot of computation. Then he will produce the nonce. So we can clearly verify. We grab the content of the block, the previous block hash, and we get his nonce, and we put it in the text. That way we can verify that he actually solved the problem. So that's a problem that's easy to verify but hard to solve. So it's hard for the miner to find the nonce, but once he has the nonce and he give it to us, we can all verify that he solved the problem. So it's basically not a mathematical equation, or he tries to solve a specific question. He just tries different numbers as a specific field in the block, so he can get a specific hash message. Is it clear now?
Okay, thank you. I got it.
Okay, perfect. So let me get back to the slides. Okay. So yeah, let's go now to the blockchain trilemma. So in the blockchain trilemma, we have three main criteria, which are decentralization, security, and scalability. So decentralization is basically having the maximum amount of nodes in the network. So the more nodes we have, the less amount of centralization we have. So and the harder it gets for a network to be attacked. So if we have, for example, 3 nodes, if 2 nodes act malicious, they will be the majority, and the blockchain will not be secure. If we have 4 nodes, if two nodes or 3 nodes try to compromise the network, it will be easy for them. So that's what we call the 51% attack. So if you ever hear about the 51% attack, it is basically for malicious attackers to have more than 50% of the consensus. So basically, attackers are or malicious persons are more than the credible persons or the credible nodes in the network. So the more nodes we have, so if we have, for example, a million node, we will have less chance of getting attacked. So it's kind of hard for an attacker to get 50% of a network that of the computation of the network that has, for example, a million nodes. So the more nodes we have, the more decentralized we are, and the more secure we are. And basically, the security aspect is the amount of of computation that you will need in order to attack the network. So if you have a lot of computation, the more computation you have, the more chance you have to attack the network and to produce false statements. And when it comes to scalability, we basically measure it by the amount of transaction that we can support in a second. So a specific block has a limited number of transactions, so we cannot include a million transactions in one block. So that will get the block size so high, and we will be basically enforcing a lot of load in the network. So for the decentralized and the secure network, we have, for example, Ethereum, we have Bitcoin, and some other networks. So those basically focus on decentralization and security. The blockchain trilemma says that you can only get two of these aspects. So Ethereum and Bitcoin are decentralized, they are secure, but they are not scalable. So the amount of transactions that can be executed by the layer 1 Ethereum or by Bitcoin is so limited. So the system is not scalable. So we cannot get to the amount of transaction that's executed by, for example, other payment methods like Visa or MasterCard. There are other blockchains that mainly focus on scalability, but in the process, they sacrifice either decentralization or security. So, for example, there is Binance Smart Chain, or what's called the BNB chain, and it mainly focuses or sacrifices decentralization, but it also has security and scalability. So they can execute a lot of transactions in the time, but they have a set of validators that are selected. So you cannot be a miner in. Not everyone can be a miner, so you have a limited number of 21 validators that can be miners in the network. So it is basically a centralized design, but which allows us to execute more transactions. And there are other networks that favors, for example, decentralization and scalability. For example, like Solana, etc., which can execute a lot of transactions, but it's easy to attack it's easier to attack the network. So the blockchain trilemma says that we cannot have everything at once, and there is a lot of research to overcome this trilemma. And for example, in Ethereum, we said that it's decentralized and secure. Now they are trying to make it scalable by using multiple changes in the network, but also without sacrificing the decentralization and the amount of security that we have for now. So scalability is increased in many ways, such as changes that are being introduced in the network itself, such as Danksharding, which there is a lot of research about, and which will be implemented in Ethereum in the future. There are layer 2 solutions which basically execute on top of Ethereum. There are a lot of applications which are for example, there are rollups, plasmas, sidechains. There are a lot of scalability solutions that are trying to solve this trilemma and also make the blockchain scalable, and also let it be decentralized and secure at the same time. So for those of you that are interested to continue in this field, this is a very good research area that you can work on in the future. So how is state stored in the blockchain? So for example, if I have one Bitcoin or 10 Bitcoins, how does this implemented in the blockchain, or how is it stored? So there are two models that are famous in the field. There are other models, but the main ones are the ones that are produced here. So the first one is the UTXO model. The second one is the account model. So I would like to make an analogy in order to make it simpler to understand. So the UTXO model is kind of similar to how cash works. The account model is kind of similar to how bank account works. So let's start by account model, which is the simpler one. So in account number, we basically store all the balances of all the accounts that we have in the network. So for example, in the block N, we have an account A that has a balance of T0. If in the next block we will have some transactions, and in the state N+1, the account A balance will be changed to T1, and also the same for the account B. So here basically we associate the account with its number of tokens. It's like a bank system. If you go to the application of your bank account, they will say to you that your account has, for example, $100. If you get, for example, you receive money, it will be updated after this transaction to, for example, if you receive another $100, it will be $200. So it is basically kind of similar to how the banking accounting works, but this is used in the blockchain field. So it is much decentralized and much better as an approach. So it is basically storing the state of each account in each state and after each modification. So that's how the account model works. Let's now move on to GTXO model. By the way, the account model is used for many blockchains such as Ethereum, Binance Smart Chain, etc. And the UTXO model is the one that is used by Bitcoin. So it is different from what is used in Ethereum, etc. So the UTXO model is basically just like cash. So in order for me, for example, to have 100 Bitcoin, I have to basically like have a proof that I already received previously 100 Bitcoins. Is there a question? Well, the session video we share. Okay, so that's for the organizers. So for the UTXO model, as I said, it's kind of similar to the cash. So for example, if I want to say to you that, or if I want to spend $100, I have to have a paper of $100. And for example, if I want to spend it and buy, for example, something that costs $50, I have to give you my $100, and you will give me a new paper of cash, which is $50. So basically, it is the same for Bitcoin. So if you want to spend, if you have 100 Bitcoins and you want to spend 50 Bitcoins, you have to provide me that with a proof that proves that you have received before 100 Bitcoins, and then after the transaction, I will give you back your if you use, for example, if I send to Alice 15 Bitcoin, I will be provided back with a new UTXO that costs $50 as an exchange, for example, or as a change. So it's kind of similar. I try to make this analogy to make it simpler to understand. And the UTXO changes for just like the account model changes from state to state, or as we can say, from block to block. Do you guys have any questions concerning the account model, the UTXO model, and the differences between the two? Okay, so if there are no questions for now, I guess it's clear, and feel free to let me know if you have any questions. And yeah, now we can move on to the next thing, which is smart contracts. So as we said, Bitcoin was the first application of blockchain in the space. So the white paper was produced in 2008, and blockchain and Bitcoin started in 2009. So Bitcoin is very good. It is decentralized. It is secure. We have also immutability. So no one can change in the blockchain due to the nature of hash functions. So if, for example, I try to change the hash of the previous block, I can be detected, and everyone can detect that I try to manipulate. I try to manipulate things. and I will get punished for that, either by losing my computation work for nothing, or losing my stake when it comes to the context of proof of stake. But this is very good, but it's kind of limited. So Bitcoin is just built for financial transactions. You can just send money and receive money, and that's it. So it is kind of the same example as a calculator. You cannot do anything too cool with a limited calculator. So if I have a machine that calculates, for example, the sum of numbers, I can only calculate the sum of numbers in this using this calculator. But the main things that we need are some general purpose applications. So it is like the evolution from having calculators to having computers. So calculators are just used to compute some simple tasks. That's the analogy of Bitcoin in this context. So Bitcoin is just used for sending and getting the money. But when the computers were invented, they provided us with a lot of capabilities, with a general purpose. We can build anything or any program with computers. This allows for much for a big area or creativity in the space. So when computer were produced, you can literally perform any tasks, and it allowed a lot of creativity and a lot of project launched after the launch of computers. They started to provide operating systems. For example, people started developing software, for example, for writing documents, for playing games, for everything. So this is the evolution from calculators to computers allowed us to have more general purpose applications, or basically a machine that can be used to implement many things and allows more creativity for developers in the future. This is the same analogy between Bitcoin and Ethereum. So in 2012, Ethereum started, and Ethereum is a blockchain that we said decentralized and secure, etc. And it has a lot of the same things that Bitcoin has, so you can transfer money, but it also came with a new functionality. So Ethereum was presented by Vitalik Buterin, which is basically one of the co-founders of Ethereum, and he is very known in the space, and he is still active in the research field. So Ethereum comes with a general purpose or allows for general purpose applications. So it is not just financial transactions. This where the smart contracts concept was introduced. So smart contracts are basically a piece of code, just like Python code, JavaScript code, etc., that can be executed. But JavaScript and Python, PHP, etc., those are executed in a centralized server, and we get the output. But smart contracts are executed everywhere in the nodes. So basically, instead of the miner just verifying the transactions and the balances, the miner or the validator executes the smart contract, executes a code, and he verifies that this code was executed correctly. He gives us the output of the code, and everyone else can verify that the miner actually executed the code as it is. Is there a question? Okay, so that's just a response. So yeah, smart contracts are a piece of code that can be executed in blockchain, and this piece of code allows for creativity and allows for many general purpose applications that that came after Ethereum was introduced, and there were other blockchains that were invented after Ethereum that also supported general purpose applications. And now there are a lot of blockchain networks that support this mechanism of smart contracts. So as I said, a smart contract is a piece of code that's executed, and it basically assures that a specific agreement between many parties, and anyone can execute this code. So anyone can deploy his own smart contract, and everyone can develop a specific smart contract. Everyone can call any specific smart contract, so we can all use any smart contract we want without any censorship resistance. So For example, for the case of governments where they, for example, as China prevents the access to Facebook, for example, this is basically censorship. So they basically restricting users from using a specific program, and it is basically the reason of that is centralization. So the government has full authority, etc. But when it comes to blockchain, we have censorship resistant. So everyone has same power. No one can prevent you from accessing anything in the blockchain. So you can always call anything you want in the blockchain, and no one can restrict you except if it is included in the code. So we will be seeing some examples of more smart contracts in the next phases. Do you guys have any questions concerning smart contracts before we move on to the next part? So the first section, this is basically, any questions?
Yeah. Just want to ask you again the summary. I was a little bit busy, so if possible, you can repeat me some summary about it to get an idea about the smart contract.
So a smart contract is basically a piece of code that is executed in a decentralized network. So it's not like Python and PHP code, which is executed in a server. So smart contracts is executed by the miner, and then anyone can verify that the smart contract was executed correctly. So we use smart contracts to extend the functionality of the blockchain. So as I said, Bitcoin just supports financial transactions. You can send money, receive money, but in smart contracts, you can basically create code that can do everything you want, and in a Turing complete machine. So you can perform any set of actions that you want in a specific smart contract environment. Is it clear?
Thank you.
Okay, so I guess this is the end of the first part, which is the introduction about the blockchain technology and how it works from a high overview perspective. So now we will be moving on to the next thing, which is smart contract development. So Ethereum allows, as we said, for general purpose application, anyone can build his own smart contract that can do anything you want, and everything is transparent, immutable, and verifiable by everyone. So the next phase will be about smart contract development. How can we develop smart contracts? What are the languages that are used, etc. So first, in the context, we will be mainly focusing on Ethereum as it was the first application, and it is still the most famous or the most commonly used blockchain network. And there are a lot of blockchains that are much different from Ethereum, but those will be the next phases if you want to complete or to have to explore new ecosystems. So in Ethereum, we have what we call an Ethereum virtual machine, or as an acronym, it's EVM, Ethereum virtual machine. So for those of you that are familiar with Java, it's kind of this similar concept. So in Java, you have the Java virtual machine, which is the JVM, and that's where Java code is executed in a specific environment. So this is the same case, but in Ethereum, and we do not have the same language, which is Java. So in the EVM, we execute what we call a bytecode. So a smart contract is basically can be written in many high-level languages, but after that, it is executed to bytecode. So bytecode is just a low-level implementation of the smart contract. So the EVM have multiple components. So do not get overwhelmed by this architecture. So it is much simpler, and if you don't understand something of it, you can ask questions, and it's fine. So we will be covering a lot of examples, so you can guys understand how it works exactly. So we have many components. So we have the virtual ROM. It is basically where the EVM code is stored, or the bytecode that I talked about. So it's basically the code of the smart contract in the bytecode format. And this place is immutable. So once you deploy a smart contract with a specific code, you cannot change its implementation. So a smart contract is is natively built to be immutable. So no one can change the code of the smart contract. Then we have the storage, which is basically a space just like a hard drive where we store persistent information. So we can basically make an analogy of the EVM just like a computer. It has RAM, which is memory in this case. It has the RAM in the computer is erased after you shut down the computer. The same thing in the EVM, but after the transaction. So after you execute a code, the memory is deleted. So if you want to store something in the blockchain and you want it to be persistent, so you can use it in the future, you have to store it in the account storage. So it is basically just like the ROM or the hard drive in the context of computers. So it is used for persistent storage. The stack and the program counter and the gas available are quite complex, and we can talk about them later. It is basically you can understand that those components are used in the execution of the code. So for now, we do not need to get into low-level things and how things work from the lowest level. Let's first introduce how we can develop smart contracts, etc. Then we can move on to this complicated part. So all you need to know is smart contracts are finally compiled into a bytecode. This bytecode is immutable. It cannot be changed it is stored in the blockchain and cannot be changed. Then we have a part which is called the storage. It is less just like, as I said, hard drives or the hard drives of servers that we know in centralized parties. But this is a hard drive that is kind of shared between everyone, and it is verifiable to be accurate. Is there a question here before moving on? Okay, so if there are no questions for now, we can move on to the next thing. So in Ethereum, there are a lot of, there are mainly two programming languages. There is something that we call Solidity and something that we call Viper. So those are high-level languages. Solidity is similar to the syntax of JavaScript. So if anyone is familiar with JavaScript code, you will be able to see that there are some similarities between JavaScript and Solidity. And it is basically due to the fact that Solidity is built on ECMAScript. So ECMAScript is the base of the JavaScript, and also it was the thing that was built, or what was used to build Solidity. So Solidity is based on ECMAScript, just like a JavaScript. So the code is similar. We just have some added features in order to support blockchain execution. So we can move on to do a little hands-on lab. So I will be sharing a different screen. Okay, can you see guys my screen?
Yeah, we can see it.
Okay, so we will start to develop a simple contract in the Solidity language. Okay. So basically, the first thing that we start with is the Solidity pragma. So the first thing that we start with is providing the Solidity version that we want to work on. So Solidity has many versions. So there are a lot of upgrades into the Solidity compiler over time, and each version supports multiple additional features, and it also newer versions fix bugs that were existing in the previous ones. So the first thing that we start with is providing pragma, solidity, and we say the number of or the exact version that we want to work on with. After that, we provide a keyword which is called contract. Then we say the name of the smart contract that we want. So let's name it, for example, first contract. So as it will be the first contract you will be developing. Then we open those brackets, and we can now write more Solidity code, which will basically state how our program works. So in Solidity, you can just declare variables. So we will be basically developing like a counter. So we will have a variable that will start from 0, and we can then increment this counter as we want in this function. So this is just a simple example, just to get you familiar with how Solidity works. So the first thing before declaring a variable is declaring its type. So there are a lot of types in Solidity. There is a type that is called unsigned integers. There are integers. There are addresses of Ethereum accounts. There are you can store bytes. You can store multiple types, and you can see that in all the types in the Solidity documentation. So, for example, we will be using uint, which is basically an acronym for unsigned integer. We can say the visibility. So we can, if we want it to be public, we can say public. If we want it to be private and not read by anyone, we can specify private. Note that this private is not actually doesn't mean that we cannot see it. It only means that there won't be a getter for it. So we can even see private variables in the blockchain. So sensitive data should not be stored in either the contract or the storage of the contract. So even if the variable is private, we can still get it from the storage slots. So let's make it public for now, and let's call it counter. And here, so we have the type, we have the visibility, and we have the name of the variable. And just like JavaScript, we use semicolons in order to end the line. So for example, so then we will have just like the classes. So if you are familiar with project-oriented with object-oriented programming, so you will have a lot of context in here. So the first thing that we can say is to have a constructor. So basically, a constructor is used to is a function that is called only one, and it is called in the step of deployment of smart contracts. So if we deploy a smart contract, the first thing that will be executed, if we deploy it, it will be executed. The code will be stored in the blockchain, and then we will execute its constructor in order to initialize the state. So it is basically a keyword, so you have to call it a constructor. So and then you can specify here if you want to specify any arguments. So let's say that we will be having an initial value of counter. So let's have an argument which will be the initial counter. Then we can perform any operations that we want. So for example, we want to initialize the counter variable, which is stored in the storage with the argument that we will be providing. So let's initialize counter into init counter. So that will be the first thing. So here you can see if you have any errors. So constructors. So if you have any errors, it will be specified here, and you can read the exact error in order for you to deploy the smart contracts. So yeah, after that we can have multiple functions. So for example, we want a function, so we can call it to increment the counter. So we basically specify the name. Let's call it increment, and let's specify the visibility of this increment. let's make it a public method so it can be called by anyone. And after that, we can just specify the counter and mention plus plus so we can increment it. So basically this function increments the counter that we have. And we can have another function, let's call it decrement, which will be public. And we will
hello.
Any questions?
Yeah, good afternoon. I'm sorry, I have a question.
Yeah, sure.
I missed some of the last parts when we started on the remix. I wanted to ask, what are we building now, like the program?
Yeah, sure. So here we are just trying to build a simplistic contracts just to get familiar with Solidity. So
Okay.
here I am in the Remix IDE, so you can access it in the remix.ethereum.org. So everyone now can access it and code along with us. So we are basically trying to build a simple contract that has a variable which is called counter, and we can increment and decrement this variable. So this is just a simple example, just to get familiar with the language. And when it comes to real world applications, smart contracts have more complex code. So it is basically implementing a use case. So for example, there are smart contracts for exchanges, for example, assets. So if you want to swap a specific token to a specific token, there are programs that support services just like the financial services that are supported by bankings. So we can, for example, have a contract that implements non-fungible tokens, NFTs. We can have our own token that we can create. Basically, Solidity or smart contracts allow us to implement general purpose applications, which we can have our own creativity, just like a regular code. So with for example, Python, PHP, and all those languages, you can implement any kind of web application you want. It is similar here, just we add a layer of decentralization, security, immutability, and also transparency. So that's the case. So in this example, we are just trying to get familiar with writing smart contracts in Solidity. Is that clear?
Oh, thank you so much.
You're welcome.
Cheers.
So yeah, that's let's make that our for example. Let's for example have a function. So that's how we declare functions. Just the keyword function. It is similar to JavaScript. We provide the name. Let's call it, for example, reset, in order to reset the counter, and let's make it public. And let's here, for example, assign a value of 0 to the counter. So we have an increment function, so we can basically increment our counter. We have a decrement function, so we can decrement it, and we have a reset function, so we can get the counter back to 0. So in order to deploy it, we go to this section which says deploy and run transactions. And Remix is basically a development IDE. It's basically used for developing new smart contracts. So here it gives you a special environment. So it is basically just a little network or a little blockchain network running just on your machine. It is basically used for testing purposes. So before you deploy your smart contracts to mainnet networks, which are Ethereum, BNB Chain, Phantom, etc., you need first to test those contracts and verify that they are working correctly. So as I said, the code of smart contracts is immutable. So if I ever deploy a smart contracts, it cannot be changed. So if I want to change the logic of the contract, I have to deploy a new one, and it will have a different address to access it. So in order for us to deploy the contract, so let's remove here the constructor, or we can comment the constructor just for simplicity, and we can get it back after. So we just click deploy, and it will deploy the smart contract in our local environment. So we can call the contract, see what it does, and verify that it's working correctly. So here we'll have a section of deployed contracts. Every contract that we deploy in our local network can be seen in this section. So here we have access to a lot of things. We have access to the counter. A counter, basically, if you make it public, you will have basically natively a getter function, so you can see the value of counter. So here we did not initialize the value of counter, so it gets the default value. The default value for an inside integer is a counter, is the default value, which is 0. So here we have a counter that is initially initialized for 0. If we call the increment, it will be 1. If we call it once again, it will be 2, and we can play around with this variable and get its value after. So if we decrement it, we will notice that it gets back to 0. If we call the reset, it will get directly back to 0. So here it is. So this is just a simple example, just to introduce how Solidity works. Of course, there are a lot of more complex examples, which will include how smart contracts can call other smart contracts. So composability is a very good feature, both in Web 2. So when we have web applications, each web application can call, for example, APIs for another web application, and this is what allows the web to work. So composability and cross interactions between different web applications, it what made the internet a cool thing. So we also have that cross chain or not cross chain, but cross calls between contracts. So from our smart contracts, we can call any smart contract that we want, and it can be implemented simply in Solidity or any other language. Do you guys have any questions for now? Okay, so let's have some 5 or 10 minutes, so you can try to develop your own smart contract. You can reach to, or you can go to remix.ethereum.org. You will have the file explorer. You can create a new file, call it, for example, contract.sol, and follow the same instructions and deploy your first Solidity smart contract. Okay, so let's. I will give you 5 or 10 minutes to do so. If you encounter any technical problems or something doesn't work, feel free to let me know, so we can target that together. I will keep the screen so you can see the code. You can develop this. You can specify the same code, or you can create a new code that does a specific tasks that works for you, for example. So you can implement some code that performs the sum between two numbers, etc. So you can implement any kind of logic you want. And if you have a hard time figuring out how you can do something, you can unmute your mic or let a message in the chat so I can help you along.
Hello, guys. How is it going? Did you manage to deploy the first contract? What did you create? Feel free to let me know your feedback.
I have a question.
Yeah, sure. What it is?
Yeah, on the second line of code, the version,
Yeah,
do we type it or
I do not hear you well. Can you please repeat?
do we type the version or do we have to use the same one as you?
I didn't hear you well. What's it about the version?
Uh, is it generated or do we have to type it?
No, you just need to specify a specific version. So, for example, you can just use this exact version as an example, or you can choose any version that you want. So it really depends on the use case. So each version has its own additional features, additional security measures, etc. So just specify it like that, Pragma, Solidity, and you can specify the version. You can even remove that if you want. And it will still compile correctly. So in order for after developing your contract, you need to compile it. So you compile the code. After it gets compiled, then you go to the deploy section. If you do not have a constructor, you'll just click deploy. If you have a constructor, if we increment it, we compile the code. You will have to specify the arguments that you gave to the constructor. So after deploying, you want to deploy the first contract, you want to initialize each stage. So as we said, the constructor is executed in the deployment process. So if you want to deploy the transaction, we need to include all the arguments that are given to the constructor. So if you want to initialize our counter with a specific value, so we can just say 11 as an example. So here it is. So we will have the initial value of the counter as 11. After that, we can just increment it, decrement it, and you will have the same effects. We can reset it to 0. So yeah, that's pretty much it. Did you manage to do that, guys? Collins is raising his hand. Do you have any question, any progress? Okay, so I guess if there are no questions, we can continue. So yeah, as we said before, smart contracts is an innovation to make general purpose applications possible. We have seen an example of a Solidity code that does a simple task, but it allows for many additional features. So for further resources, you can check the documentation of Solidity, and there are a lot of tutorials out there that present the full functionality of Solidity and how it works. So the next thing we'll be covering is the development for frameworks that are widely used and famous in the space. So just like any type of code. So if you want to develop in PHP, you can develop in native PHP, etc. You can also use development frameworks in order to just to help you and make it easier. It gives you some already built libraries that you can work with directly. It uses specific structures, so you separate your logic in a specific way. Same example with Python, with Django and Flask. So you have, with every programming language, you have many examples of frameworks that help you perform and implement your code and give you access to already existing libraries, so you do not have to reinvent the wheel. So you can use the libraries that were created by experts, and you can use them to create your own functionalities. Excuse me. So yeah, basically in Solidity we have multiple frameworks. We have what we call Hardhat, Foundry, Truffle, Brownie for Python. So we have a lot of frameworks that help us basically move on with the development and implement our functionalities. So the Solidity code doesn't change, but the development frameworks helps us with additional tasks, which are the first thing is unit testing. So when it comes to unit testing, Hardhat, in Hardhat you can implement unit tests for your functionalities. So for example, for our simple example counter, if you initialize the value of the counter to the value of 7, you will call the increment, and normally the value should be 8. But if there is a security bug or something that doesn't work properly, you should be able to detect it. So unit testing is generally used in multiple projects, either in Web2 projects or Web3 projects. So it is basically a way to assure that a functionality works as expected. So if I increment the value of the counter from 7, then I should be expecting an 8. So in the background, we will basically be calling the function of the counter reader. We will see it, and we will call the increment of the smart contracts. Then we will get the new value of the counter, and if it matches our expected value, then we can say that the test case is successful. So unit testing is widely implemented and used basically in every programming languages, and Solidity is not an exception. So in Hardhat you can write unit tests in either JavaScript or TypeScript. So you basically write JavaScript or TypeScript code just to call your contract and test it. And there is another framework. Though Hardhat and Foundry are the most famous. So Foundry is relatively new compared to Hardhat. Foundry, basically you write your unit tests using also Solidity code. So you basically create your own contract, and you create an additional contract that is used for testing, and you can import many libraries that are existing in order to help you prove your test cases. You can impersonate some address to cover a specific edge. So in the example of counter, it's kind of simple. So the unit testing value is not doesn't look that much valuable, but when it comes to real world applications, and when we have a more complex Solidity code, then the value of unit testing is very handy. So it basically helps us to make sure that we haven't made any inaccuracies or any mistakes, or we haven't left any vulnerabilities. So as we will present in the upcoming sections, security is important. So Solidity is just a programming language. You can still write Solidity code, and you can still introduce vulnerabilities when writing it. So the blockchain is secure, it's decentralized, but It's not a silver bullet. So in order for you to have a secure smart contracts, you don't get that just by developing using Solidity. So in order to do that, you have to follow many best practices, implement unit testing, audit your protocol, look for vulnerabilities, and there are a lot of common vulnerabilities that some developers make, and they can be so critical when it comes to the blockchain world, as there is a lot of money in the in the space. So just in the previous year, there were a lot of approximately some around two to three billions of dollars that were lost in the blockchain just due to some vulnerabilities in the codes of or the logic of the smart contracts. So smart contracts are a very good very good way to implement general purpose applications, but they are not natively secure. So you need to follow best practices, you need to be a good developer, and also you need to understand the security mechanisms or the common vulnerabilities, and you have to implement very critical measures in order to prevent those vulnerabilities. And it's the same as if you are writing the code of a web application, it also has vulnerabilities, just like we have XSS and SQL injections in web applications. Also in Solidity, we have some common issues that you need to avoid, and it's even more critical in the blockchain for two reasons, which are that the code is immutable. If we produce an incorrect code, we will not have the option to modify it and to fix the bug. And also the fact that there is a lot of money at stake. So if a contract has a lot of money and it somehow there is some left condition that is not checked, there is a reentrancy that we will talk about later. The contract can lose all the funds and it can be extracted by a hacker. So is everything clear for now? Okay,
Yeah,
so
it's clear.
okay, perfect. So development frameworks, as I said, help us write unit tests, which can help us secure our, or just verify the correctness of our functions or our Solidity code. It also helps us with the automation of deployment. So if you want to develop and to deploy your contract into a local environment, you can deploy a script that does that simply. If you want to automate the process of deploying into a real world network, you can do that also using Hardhat or Foundry, etc. So those are mechanisms that are widely used in order to help the developers and make them write fully functional and secure smart contracts that achieve a specific task, which can be a simple one or which can be a complicated one, depends on the exact use case. So we'll be moving on to the part of smart contract security. So smart contract security, as I said previously, is so important and even more important than securing, for example, a web 2 application or a simple web application. So smart contract security is more critical as we cannot fix the bugs directly. So the smart contracts are natively immutable. We cannot change the code. Therefore, if we leave a vulnerability in the code and then deploying it, we cannot fix it after that. Also, we are dealing with blockchain. We are dealing with a lot of financial transactions, so a lot of money can be lost in the process. So we'll be first introducing some common vulnerabilities that are existing in smart contracts. So the first one is called reentrancy. And let's focus now on the Solidity part. So for example, we have a contract A and a contract B. So there is a case, for example, if we want if we have, for example, a function that checks the balance. So I want to send, for example, a specific 10 tokens from the token A to a specific person. Then we send the funds and then we update the balance.
And let's suppose that those funds are Ethereum funds. So before sending the Ethereum from a contract to a user, so, we check the balance. For example, I have 10 Ethereum in the contract A. I call this function. It checks the balance. It checks that I have the 10 Ethereum, and then it sends the funds. So if the target is an externally owned account, which is just the wallet, it will function correctly, and then it will update the balance. It will basically reduce my balance, and it will subtract subtract 10 ether. So it will basically update my balance, and everything will work correctly. But if the target that we want to send the funds to is a contract, natively, if we send Ethereum from a contract to another contract, basically we are calling a function in the other contract, which is called the fallback functions. So if we send Ether to the specific contract using a contract A, we will basically execute some code. So after sending the funds, if the contract B is malicious, it can implement some custom code in its fallback function in order to bypass the checks. So let's redo the execution process. So as I said, I have 10 Ethereum. The contract, for example, has 100 Ethereums. I have 10 Ethereum in the contract. So the contract first, after I call this specific function, it checks my balance. It verifies that I have the 10 Ether, which indeed I have. It then tries to send the funds to me, and I am the contract B. And in the contract B, I can call back the same function. So here, as we can notice, the update balance is called in the last phase. So if we send funds, then call the fallback function. The fallback function can also call this function. It will recheck my balance. It will still be 10 Ether. So the balance is not updated yet. Check the balance. I have 10 Ether. It will send me the funds once again. It will send me another 10 Ether. And my fallback again will call the contract A. It will check the balance. It will send me another 10 Ether. So now I have 13 Ether. Meanwhile, I only have 10 Ether in the contract. So that way, before the balance is updated, I can exploit the fact that the balance updated in the last step by just draining the contract and calling back the same function. Is that clear, guys? Feel free to drop any questions if you have any, or if anything is unclear, let me know. Is it clear, guys? Okay, since there are no questions, I guess we can move on to the next one. So, okay, perfect. So the next one will be integer and integer overflow and underflow. So this is not just in Solidity. This is also the case for some other languages. So basically integers are integers are encoded in bits or in bytes, if we want to say. So we have a limited amount of bits that are allocated into storing an integer. So for example, the maximum that we can allow to an integer in Solidity is 256, or in bytes it's 32 bytes. So we have this amount of space, so we can have an integer starting from 0 up to 2 over the power of the number of bits minus 1. So let's say, for example, that we only have 4 bits, just for the sake of simplicity. So if we have 15, so we have 4 bits. So in binary, it's 1111. if we try to increment this value, we will reach the max of the integer. So natively, in some Solidity versions, we will get back to 0, since we will be incrementing this binary number by 1. So it will be actually 1 and 4 zeros. And since we only have 4 bits, the first value of the 1 will be removed. So that's how overflow works. And the same for underflow. If we have 0 and we go with a -1, we will get to 15. So this is a simple example in 4 bits, and it can also happen in any number of bits. This operation can cause a lot of loss in when it comes to phones, and it depends on the use case. So in Solidity version before 0.8, so in 0.8, if your transaction will cause an overflow, the transaction will natively revert, and it will be just like the transaction did never execute. So natively in Solidity version 0.8, it prevents this bug of integer overflows and underflows. But in Solidity versions 0.7 and below, this bug is present, and it actually caused a lot of loss in a lot of blockchain protocols. Is that clear? If it's clear, we can move on to the next one. Feel free to let me know if you have any questions, guys. Okay, perfect. So let's now move on to the next bug, which is basically a broken access control. It's a bug that's present in all programming languages and all web applications, and it is the same for smart contracts. So there are some functions that are you can restrict basically in the code. You can say that, for example, only the deployer of the contract or the owner of the contract can call this function. So it will be a function that updates a specific fee. It will be a function that does some operations that should not be done by other ones. So that's what we call access control. So there are a lot of protocols, and when the protocol gets complex, it's easy to miss those tricks of access control. So you can leave some functions that should not be meant to be called by anyone. You can leave them exposed, and they can be called by an attacker, which can cause a lot of harm to the protocol. So this is a basic bug, but it's a common one, as the code is developed by humans, and as the protocol gets more complex, it's more probable to make this mistake. So if you have a list of multiple contracts which have cross contract calls between them, and the system is complex, it's easily can happen that you miss some access control, or you leave a function that's exposed to anyone, which should not be the case. So that's a simple one, as it is the same for web application and also smart contracts. So missing input validation. So in some contexts of some functions, you need an input that's specific, or for example, an input that can be between 0 and 100. So if you leave that open to the user, he can specify values that are not under the ranges that you want, or the input does not match what's expected. So you should always verify your inputs and verify that those inputs match with the logic of the specific contract that you have. So input validation should be performed in any argument. So anyone you should also always expect anyone to call your contracts, and he can manipulate the inputs in a way that's not verified, and he can cause a lot of edge cases that were not covered either in manual testing or in the unit testing and automated analysis. Race condition, it is basically coming from the fact that the transactions are not executed sequentially. So if I send, for example, Alice 1000 Ethereum, and Alice sends, for example, then Alice sends 5 Ethereum to Bob, I cannot guarantee that those transactions are gathered by order. So only the miner can control the order of transactions. So there is no restriction for the miner to include the transaction order in to be specified chronologically. So if you execute transaction A, another one executes a transaction B, we cannot deduce or we cannot guarantee that this transaction will be included first, then or before this transaction. So the order of the transaction is specified by the miner, and this can cause a lot of issues. So for example, if I change the variable that you will be using, so for example, if you find the variable that is equal to 10, and you are, for example, if someone is selling his Ethereum for 5 of some specific token, I can see that and I like that offer, then I execute a buy operation in a specific transaction in a smart contract, of course. Then after that, the buy or the seller can change the value of this variable. So it's now just 1 Ether for 5 tokens. If the miner flips the order of those transactions, I will end up buying with the latest price, which is not the one I saw before executing the transaction. So it is basically a race condition, and the miner can manipulate the order of transaction as much as he wants. So it most likely depends on the gas price and that aspect, but we cannot have any guarantee that a transaction will be included before this one, and this can cause a lot of harm. So here we have an example of a simple variable that is equal to a method that increments it, and we have a method or for doubling it. So for example, if we have the variable that is equal to 5, normally if I call the method x, it should be multiplied, and if multiplied by 2, and if I call y, it will be incremented. So for example, if I call the method, if I see that the new value of the a is 6, I expected the product to be 2, but if the transaction of the transaction x performs the operation on the old value, it will have 10 as a value, then we will be incrementing. So the order of you should always consider that the order of transactions is not guaranteed, and you should always check for that as a smart contract developer and also as a smart contract auditor. Is that clear, guys? Do you have any questions before moving on? Okay, so I guess we can move on to the next one. Next one is the insecure use of delegate call. So there are a lot of ways to call other contracts. So there is call and there is delegate call. So basically, using a call, you basically use from a contract from the caller contract to the target contract. You basically use the address of the contract as the message.sender. The message.sender means who is the caller, and the message.value means how much ether it is transferring. So if the caller contract calls the target contract, the message.sender in the target contract will be the caller, and the message.value will be the message.value that is sent by the contract. But if we use delegate call, a wallet can call the contract, and this contract can delegate the call then to the target contract. So delegating the call means that it is keeping the same message.sender and the same value of ether. So it is basically not changing the caller. So if we, instead of delegate call, we use call, here the message.sender in the target contract will be the caller contract, since it is the one that called it. But since we have an external owned account, it is basically just when using delegate call, it is just acting just like the external owned account to the target contract. And this can cause a lot of bugs, since the storage that is modified in the delegate call is the storage of the caller contract. So the target contract is basically just a piece of code that is executed in the caller contract. So it's just like you're grabbing a piece of code from elsewhere to be executed in the caller contract. Is that clear? Feel free, guys, to let me know if you have any questions. So there are a lot of examples of these bugs. There are a lot of CTFs, which are capture the flag challenges that you can use in order to apply those vulnerabilities and try to exploit them of course in a good way and in an environment that is meant for that. So you can get your hands on when it comes to that. I will be given some resources of CTFs which you can use in order to learn more about those vulnerabilities in a practical way, not just in theory. So if there are no questions, we can move on to the next one. So the next one will be rounding errors. Rounding errors is common in when performing integer division. So if, for example, there is some operation in the code that executes an operation of division between two integers, which are, for example, 3 and 2. So if we divide 3 over 2, we should normally expect 1.5. So that is the accurate result. But since we are performing integer division, so Solidity does not support floating numbers and double numbers. So there are only integers and unsigned integers. So if we perform 3 over 2 in Solidity, it will give 1 instead of 1.5. So there are no floating numbers, and we should always account for that as blockchain developers and also as auditors. So if you perform any division, you should always expect that the floating part will be removed. So you should account for that by either multiplying by a precision factor or changing your logic and adapt it to support the fact that rounding errors are common. So this issue exists in a lot of programming languages, and it is the same for Solidity, since it doesn't support division or it doesn't support floating numbers. So it only supports integer division. So you should not expect the values to be as accurate as you present them. Is that clear, guys? Do you have any questions?
I have a question.
Yeah, sure.
Yeah, okay. You said that in smart contracts, the numbers already are rounded to integers.
Can you repeat, please? I didn't hear you well.
You said that in smart contract already the numbers are rounded to the integers.
Yeah.
Okay, so how, like, we can see in blockchain, like let me say activities that uses blockchain. Let's say cryptocurrency, like in Bitcoin, you can send like 0.005 Bitcoin. Is does it based on smart contract or what? Tell me, clarify about.
Yeah, there are a lot of ways to basically make use of floating numbers, but without actually storing them as floatings. So as an example, we have the concept of decimals. So let's say just for simplicity, that I want to send you 0.1 Ethereum. So Ethereum supports floating amounts. So how it is basically doing that is it is 0.1, but it is not stored as 0.1. It is, for example, if we have a decimal of for simplicity, let's make it just 4. So if you have a decimal of 4, it will be stored as 0.1 times 10 to the power of 4, which is basically 1,000. So in the blockchain, it is stored in 1,000, but when it is shown to you, it is shown as 0.5. So basically, they perform a division in the front end where they show you your amount. They perform the division between what's stored in the storage, which is 1,000, over 10 of the power of the decimal, which is 0.1. So it is stored as an integer, but there is a decimal factor that you need to divide over in order to get the final amount that you want in floating numbers. Is that clear?
Yes, so it means that when we are going to calculate it, or when we are coding it, we don't code it to appear we don't store it as decimals, but when we render it to the HTML or to the front end, we have to ensure that it is in the correct amount, or yeah, like that.
Yeah, that's basically it. So
yeah, okay.
For the case of Ethereum, I said 10 of the power to 4 just to make it simple, but in Ethereum it uses 18 decimals. So the smallest unit of Ethereum is called Wei, WEI. So the smallest unit of Ethereum is Wei, and it is 1 Ethereum is equal 10 to the power of 18 Wei. So the smallest unit of Ethereum is Wei, and you can transfer any number of ways to other tokens, and that's how it is stored in the blockchain. But when you want your balance to transfer it from Wei to Ethereum, you have to divide over the decimal, and it is most likely done in the context of front ends. For tokens that, as we said, smart contracts. In smart contracts, we can implement anything. So we can create our own token. We can not limit ourselves to Ethereum. We can create our own token in a smart contract, and we can define its own behavior in code. Very clear. That is important case to know about. Yeah, that's the case. So rounding errors are mostly common. So even though blockchain developers and auditors should know that, there are some ones that miss this edge case. As I said, when the protocol gets complex, humans tend to leave out this kind of errors, and those can cause a lot of harm and a lot of a big loss in the funds when it comes to real world applications and big protocols that owns a lot of money. So I hope that's clear. Let's now move on to the next one. Next one is sandwich attack. So it's kind of coming from the fact that we talked about before of race conditions, which is the fact that we cannot order transactions. So basically, the miners select the order of transactions over the fee that is paid. Is there a question? Okay, so as I said, the order of the transactions is most likely done by the miner, and it is using a parameter which is called the gas price, which says how much the caller of or the sender of the transaction is paying for his transaction. So most likely they choose the high payer. So for example, if I see so the transaction before they are executed, there is something that is called the mempool. Hello guys, do you hear me all? Hello?
Yes, we can hear you.
Okay, perfect. So I was talking about sandwich attacks. So as I said, the mempool is transparent to everyone. So if I want if I see that Alice wants to buy a specific token for example 10 Ethereum, and I find that token, for example, is worth 8 Ethereum in another place, I can execute a transaction and pay a higher gas fee in it. So the miner will include it first. I can then buy those tokens, and then I can sell them for Alice over with the price that she wants, which is 10 Ether. And now I made a profit of 2 Ether in the difference. So and sandwich attacks, this is basically a front run. Sandwich attacks is including basically trying to execute a transaction before someone, and there is the backgrounds, which is trying to execute a transaction after someone else. So it is basically depends on the case. There are a lot of cases where sandwich attacks comes handy, and you can change a lot of things in order to or you can exploit a lot of and get a lot of value just from performing transactions before someone else and after someone else. So sandwich attacks is including a transaction of a specific user between two transactions of yours, just to exploit some logic bug. So the one that I said about buying and selling a specific token using Ethereum is just a simple example. There are a lot of use cases where these sandwich attacks can be exploited. And as a developer and also as a security auditor, you should always take this into account and consider that an attacker can perform a sandwich attack to exploit your logic. So you have to adapt your logic in order to prevent that issue. So is it clear for you guys? Let me know if you have any questions before moving on to the next one.
What about that time of appearance on the blockchain P2P network? Is it the time that this operation will be appearing on the network? In my case, I used to think that the transaction always appears on the network forever. What is this time, like from block N to block N plus K?
So basically the time is specified by the miner. So all the transactions that are executed in the same block, the miner will specify the timestamp that he executed the block in. So after the addition of each block has a specific timestamp. So all those transactions have the same timestamp, and this timestamp does not mean that the caller executed this transaction in this specific time. This timestamp just says where or when exactly the miner included this transaction in that block. So if I say in a specific transaction, if I see in a specific transaction that it was executed 1 hour ago, it doesn't mean that the caller sent this transaction 1 hour ago. It only means that the transaction was validated by the miner and included in the block in that specific time. So we do not have a deterministic way to see in the blockchain when this transaction was submitted.
Okay, clear.
Okay, perfect. So if there are no further questions, we can move on to the next one. So in general, there are a lot of common vulnerabilities that are known, and they cannot be resumed into a single presentation. So I'm just trying to present the most common ones and to cover a lot of aspects, just to introduce you guys into this space. And there are a lot of resources out there to read more about more vulnerabilities. And also those are just examples. There are also logic bugs. So there can be an example of a specific smart contract that behaves in a specific way, and you can get some value out of it just exploiting its own logic, not exploiting some logic in Solidity or in a conventional way. So each protocol has its own logic way or logic vulnerabilities. So the next one is signature replay. So there are a lot of smart contracts that use also signatures inside the contract. So for example, if I don't have Ether and I want to transfer tokens to someone, I can give him a signature of mine that, for example, if I am A and I want to send to B, for example, a specific token, I need Ethereum to pay for the transaction. So just an example, I can give him a signed message that that he can claim these transactions from my account, and he can use this transaction, submit it to the smart contract, and get this money. So this is just an example of how signatures can be implemented in a smart contract. But this can be exploited. So if I give him, for example, if I am A and I give B a signature that he can claim, for example, 10 tokens, he can use this signature to claim 10 tokens, and he can use it once if the smart contract itself doesn't prevent him. He can use the same signature once again and once again and start claiming more tokens. So in the smart contract side, there should be a mechanism that allows a signature to be only used once. So if the signature can be used more than once, here anyone can perform a signature replay attack. So as the name says, he can just replay the signature. So he can say that the person A gave me or allowed me to claim 10 of his tokens, and he can do the same again. So the signature is always valid. So there should be a mechanism that allows for the smart contract to store the used signatures so they cannot be used once again. Sorry, is that clear, guys? Do you have any questions?
That's clear, but I have a question, not mainly on this signature replay.
Yeah.
Can there be like how does a cooperation between two blockchains work? We can have Ethereum blockchain and another blockchain aside. Like if you want to, there is EC20, and the what? We have.
Please repeat. I do not hear you well. The sound is not
okay.
clear.
How can a cooperation between two blockchains can work? Like I want to do a transaction between this blockchain and another blockchain, which have different genesis block. Like you get what I'm saying? Yeah. How can that work?
Oh, that's an extremely complex subject, which is and there is a lot of research concerning that subject. There are a lot of approaches and there are a lot of mechanisms that are already used. There were a lot of protocols that were hacked using some of the solutions. So it is basically to perform a transaction from a blockchain to a blockchain, or for example, to transfer a token that you have in an Ethereum to for example, Binance Smart Chain, you will have to use what we call a cross-chain bridge. So a cross-chain bridge is basically an entity that basically you can use to broadcast messages from a blockchain to another blockchain, and there are a lot of ways to implement it, and there are a lot of methods that are used. Some methods use what we call oracle networks in order to transfer messages between the both parties. Some tend to rely on a central server that listens to the blocks of the Ethereum, and when he sees, for example, that you want to transfer 100 of some specific token to another blockchain, he confirms that the transaction actually was executed in Ethereum. So he tells Binance to mint you a new version of those tokens in Binance Smart Chain. So there are also another mechanisms that use some advanced cryptographic schemes, such as zero knowledge proofs, such as commit reveals, etc. So there are a lot of complex mechanisms that implement that, and there is still a lot of research going on to discover the most secure mechanism or a standard way. So as for now, there is no standard way to communicate between blockchain and blockchain, and there are a lot of research out there, and there are also some blockchains that do not have a specific network. So there, for example, when we can talk about the example of Polkadot, it has a relay chain which is Polkadot, and it has a lot of other chains which are called parachains. And basically, Polkadot allows for communication between those chains in a trustless way. So you do not rely on a specific party. So this is one of the solutions of implementing a multi-chain solution where you have many blockchain networks that communicate with each other.
Okay, does that come with its downside?
It really depends on the mechanism that is used. So, for example, if we are using a centralized server, we are basically losing the decentralization value that is assured by the blockchain. So,
Personal signature, right? Personal signature.
Okay.
can you guys unmute if you do not
There is no personal signature. Turi ibintu by'ama Ethereum, ukuntu ukora website y'ama Ethereum. Rero kuri Ethereum na bya Bitcoin na bya ukaba wakiriya nyine nawe ntuzi umeze nk'iriya.
So let's wait until
They are talking about
background removes, so I can continue.
Uraguha akazi? Ko tuvuge ngo dutegereze email zigiye gukurikiraho se bagiye kuduha transport. Aga transport kajyayo hazajyamo abambere gusa.
Theophile.
Bavuze abambere.
Theophile.
Bavuze ko ariko bazarangira uko
Theophile.
bazajya.
Theophile.
Guys, you're shouting.
They may mute him. That's all.
Okay, so as I was saying, so blockchain bridges security depends really on the way it is implemented. So as I said, there are multiple approaches. So if you are we are using a centralized server to listen over the transaction of Ethereum, so we can execute those transactions in binary smart chain. This basically removes the decentralization value that we have in blockchain. So we are relying on a centralized server to tell us information, and the server can be malicious, or it can even be hacked, and we will have a lot of problems. And there were a lot of funds that are lost this way. And there are other mechanisms that implement some kind of relayers that provide those things. We have another decentralized network that is listening to those blockchains, and they perform their own consensus algorithms. Then they execute the transaction in the other chain. So it is still, there is no standard way that is completely secure and decentralized for now. And there are a lot of efforts to use advanced cryptographic schemes to make it secure and decentralized, and so we cannot have any compromises between in the process of bridging assets from bridge to bridge, or sending messages from bridge to bridge, from blockchain to blockchain.
Okay. I understand.
Okay, perfect. So now let's move on to smart contract auditing. So smart contract auditing is basically there for identifying security vulnerabilities that exist in smart contracts, and trying to report them so they can be fixed before deployment. So there are a lot of companies and entities that are providing this service. So it is similar to penetration testing when it comes to web applications. So it is kind of similar to that. So as a smart contract auditor, you are meant to act like a hacker, but in a white hat. So you just play the role of a hacker in order to find the bugs in the smart contracts. Then you report those smart contract bugs to the client so they can fix those before deployment, and so you can save a lot of funds that could have been lost if the vulnerability is still there and the contract is deployed with it. So for example, you tend to look for all sort of bugs, all those bugs that we mentioned, and there are a lot of other bugs that were not covered in this presentations due to the time constraint. There are logical bugs that are related to the specific smart contracts you are auditing. So as a smart contract auditor, you should always read the contract, understand the logic and the perspective of it, try to look for the common vulnerabilities, and also understand the logic in order to find creative ways to make the system or to let things go wrong, so you can report those issues to the clients so they can secure their own smart contracts to prevent the loss of funds. So smart contract audits requires a lot of steps. The first one is a code review. So you just analyze the code, try to look for attack vectors. How can you make the system go out of its desired way, etc. So you just try to manually and analyzing the code and looking for vulnerabilities, logical bugs, reentrancy bugs, signature replays, etc. So all sort of bugs should be considered. And there are also some automated scanners which you cannot rely on 100%, but you should use them in order for them to help you discover some things. There is a Slither, which is a static analysis tool. It reads the codes, looks for some attack vectors, but those are not bulletproofs. If the scanner does not state a vulnerability, doesn't mean that the contract is secure. So automated scanners and code reviews should be used in parallel. We cannot use only one. So Slither looks for attack vectors. Mythics uses dynamic analysis. Echidna is used for fuzzing. So as I said, for unit testing, we provide our functions with some values and see if we get the expected output. In fuzzing, we basically give our functions random outputs, multiple random outputs, like 1,000, 10,000, 100,000 of values and random values, and we try to test some edge cases. So if we verify that our function is correct, for if we give it for example the counter example, if we give it 10, we expect 11. There are edge cases where this example doesn't work. So if I give it, for example, the maximum value that can be stored in an integer and it tries to increment it, it will cause an overflow and it will give you 0 instead of incrementation. So by giving your function random outputs and over a lot of tries, you try to cover a lot of edge cases that can be missed in unit testing. So unit testing is not enough. You should always you should also include some random outputs in order to verify that your function works for all inputs, not just for one or two inputs. There is, for example, a tool called Manticore. It is basically using symbolic execution. So symbolic execution is a formal method that uses mathematics to prove that a code is behaving the way you want it. So this is kind of a bulletproof that the function does what it's supposed to do, but it is more complicated to perform symbolic execution, and it requires a lot of mathematical background and understanding of how to write specifications for your contract. So this is more for the advanced level to use a formal verification that helps you prove that a code is behaving correctly and not for just some specific outputs or random outputs. Is that clear for now? Okay, so we can now move on to the next section, which is the roadmaps. So I will be sharing a different screen. So the first roadmap is there is some noise in the background. Can you guys mute your mics?
Okay, so now let's move on to seeing the roadmap. So how to be a blockchain developer. So the first thing is to learn the prerequisites. So you should have a minimal level of computer science knowledge, how computers work, etc. Uh, in general, how basics about cryptography and how it works, and yeah, we should also learn consensus mechanisms. As we said, proof of work, proof of stake. There are other ones, such as proof of authority, proof of delegated proof of stake. So those are different approaches which are not required for you to learn as a starter. So this is more for the advanced level. So now just understanding proof of work and proof of stake and how they work is more than enough for you to start your career as a blockchain developer. So you should learn blockchain fundamentals, data structure, how distributed ledgers work, the blockchain, block genesis block height, every part of how blocks are built. Nodes, you should have knowledge about cryptography, hashing, encryption, as we said before. You should know what is a blockchain or an Ethereum address, what is the private key and public key, as we stated before. You should know the transactions, everything about the transaction, the mempool that we talked about, which is the transaction pool where the pending transactions exist, the transaction fees which are paid by the callers to broadcast transactions, the accounts, the forks, how mining works, etc. So you should always know those blockchain basics and fundamentals of how things work. So there are a lot of types of blockchain. There are public blockchains like Ethereum, Bitcoin, etc., and there are private, hybrid, and consortium for this. Those are more for industrial use. So they do not value the decentralization that much, etc. So it is basically used for verifying integrity and integrity of data and using signatures, etc. So also you have to get a little bit of information about improvement proposals. So Ethereum and blockchain do not stay the same all the time. There are upgrades in order to produce more functionalities and more standards in the blockchain. So those are called improvement proposals. For Bitcoin, it's called BIPs, and for Ethereum, it's called EIPs. So those are just upgrades over the logic of the blockchain and customizing how it should work. This is optional for the papers, so you can read the white paper and of the Ethereum, for example. The yellow paper is more formal, so it includes a lot of mathematical language description of Ethereum and how it works. You should know the blockchain, or at least the famous blockchain networks, the ones that are decentralized, such as Ethereum and Bitcoin, the centralized ones, etc. So you should also know about the type of protocols there are. So there are layer ones, and what are the scaling solutions that are being introduced in order to make Ethereum scalable. So for to make Ethereum scalable, for layer one, there is sharding, which is an advanced concept. For layer two, there are rollups which have different types, etc. So we should always be looking for the solutions that are existing in order for you to understand the ecosystem more. So the more you advance, the more you learn about niche subjects such as scaling, etc. You need to know about crypto assets, you need knowledge about finance. So if you are a blockchain developer, you will be mostly developing financial protocols. So you should understand the basics of finance and the basics of decentralized finance, which is basically the finance implemented in the blockchain. So there are a lot of things you need to know, such as tokens. What is token? What is fiat? What is a coin? What is the difference between coin and token? What is a stable coin? What is a security token? What is an NFT? What is an airdrop, etc. So those are terms that you should be familiar with. So you do not need to learn all of this information that I'm telling you in the first day or in the first starting week.
etc. So this is a continuous process. So you start by learning something by something, and you start building things and improving the things you build. So you should not see this as a step that you should learn all of this. You should do it step by step and try to improve yourself as much as you can, because the space is evolving in a high pace. So you should always keep up with the new information and with what's coming. There are all sorts of proofs, validity proofs such as zero knowledge proofs, fraud proofs like optimistic proofs. Wallets, how wallets work, how they use private keys and public keys, what is your wallet address, how is your wallet address extracted from your public key, what is the signature mechanisms. So those are things that you can learn one by one. As I said, you are a blockchain developer, you are a smart contract developer. You should know Solidity, how it works, and you should know its security gaps, so you can develop secure code. You should know all about interoperability solutions such as bridges that we talked about before, Polkadot network, how bridge works, how oracles works, etc. So as I said, you should learn about decentralized finance, how it works, how it is implemented, what are the famous protocols in the field, and also about decentralized applications. And lastly, you should keep learning. So if you learn all of this, you should always keep learning and improving your skills by seeing the upgrades that are performed in the blockchain, keeping up with the blockchain hacks that occur, so your next developed code will not have the same issues, etc. So that was it for a roadmap of how to be a blockchain developer. Is it clear before we can move on to the smart contract auditor roadmap? Do you have any questions, guys, about the directions, how we should move on?
Okay, I have a question, but not that. Yeah, okay. Question is about you mentioned the a zero proof knowledge when you were talking about the roadmap. I mean the zero proof knowledge you're talking about is that one where you show people what the procedure of a thing, but without telling them what is the logic behind the secret behind, isn't it?
Yeah, exactly. So zero knowledge proofs is a cryptographic mechanism that is used in order for you to prove a specific statement without giving much data about it. For example, I can convince you that I have a password, but without giving you the specific password. And it is applied over a lot of applications in the blockchain. It is applied in the bridging mechanisms that we talked about. So for example, for you to execute a specific transaction in the Binance Smart Chain, you have to provide me with a zero knowledge proof that you executed in the other transaction in Ethereum. For example, it is used for scalability. So I can validate a lot of number of or a big number of transactions off chain, which means out of the blockchain, and I can include them in the blockchain just by submitting one zero knowledge proof that I have calculated those transactions correctly. So zero knowledge proofs have a lot of applications both in blockchain, in AI, etc. And it uses a lot of advanced mathematics under the hood in order to perform that. Does that answer your question?
Yes, it answers. But when I came across this zero knowledge proof first, I started thinking about like those hash algorithms, like who developed them. So they convinced us that they are irreversible, and they showed us. So, but are we sure that they are irreversible? Are they one way really? But okay, that's it. Let's skip. But we can do the research aside by ourselves. But it alerted me like those SHA-256 or those algorithms, the developers, they really know how they work. Okay, so and at the end of the day, they came up with them, they convinced us that they are irreversible if you hash a text or a datum, or you can't reverse it, or it's one way. So
Yeah.
no one knows how it can be reversed, and they convinced all of us that it is true, that it is reversible. So yeah, what do you think about that? I'm not asking you to answer that question if it is reversible. What do you think about it?
We basically rely on the mathematical complexity theory. So when we say that a function is irreversible, we do not mean that we just didn't find a way to reverse it back. So it is mathematically proven that those functions are irreversible. So if you have the required knowledge of mathematics, you can just go to the exact proof, or you can just analyze how for example SHA-256 works. So, and you can really mathematically prove that it's irreversible. So if if you prove something mathematically, so you cannot except if you make a mistake in the proof itself, you cannot prove it wrong. So there is a lot of content that proves that these functions are made to be irreversible. So it's not just like that we believe that it's not or we did not find the solution in order for us to get back. So the application or the function is designed to be one way. I don't know if that answers your question or not.
Yeah, I understand. I understand. So there is I'm thinking like this. So if we have input A, similar input A, we always get the hash, certain hash, okay?
Yeah.
Always, unless it is tagged to the type. Okay. So what if we have this data, we always have this hash. Won't there be a predictability as the AI is increasing? What do you think?
I didn't hear the last part. Can you repeat?
Won't there be, like, will not there be a predictability of, if you have seen the Anders demo of the blockchain, have you used it? Like Anders demo?
There is some noise in the background. I
Hello?
cannot hear you. Sorry.
All right.
There's
So
someone that's mutation. Sure.
Okay, I'm asking like this. If we always have input A and we always have the hash B.
Yeah.
It's always like that. So won't there be a predictability since the data X provided always a similar hash? Won't there be a predictability of
yeah, I get your point. So, for example, if we have a text which includes test, we have its value, its hash value. So if we see this hash, we know that its reverse or its previous image is test. So this mechanism is used as, or what we call hashing database. So for example, if you hash the word, for example, Facebook, and you search it on Google, or you just provide the hash of the Facebook in Google, you can find that its previous value is Facebook. So when it comes to these common words that are used by anyone, we did not reverse the hashing functions, but we kind of just knew the final answer and the first thing. So, but when we get to more complex texts, you cannot really reverse it because you need to literally brute force an infinite amount of characters in order to get it. So if for example I hash 1 gigabyte of information, the amount of possibilities that you have to cover in order to brute force to find its hash. It's kind of not doable. So that's
Yeah.
why, for example, in web applications, we store the hash of the password, and we recommend for the users to not use regular passwords. If we use complex password, even if the database of the web application is leaked, the attacker can only find the hashes. And if your password is test123, he can easily find out your password. But if your password is more complex, he cannot reverse the hash to get the actual
Yes.
password.
Thank you so much. Yeah.
I have a question too.
Sure.
So it's about the layers. Would you elaborate a little bit about layers? What qualifies a network to be a layer 1, layer 2? And alongside with that, does all interoperability solutions qualify as layer 0, as Polkadot is by default?
Yes.
So what is considered layer 1, layer 2? What is the criteria? Is it the protocols or anything?
Yeah, I got your point. So when it comes to the layers, so the main blockchain networks that we have are layer ones. So Bitcoin, Ethereum, Binance Smart Chain, Solana, those are basically layer ones, and layer ones are basically the blockchains that have a Genesis block, etc. When it comes to the layer 0, as you said, those are basically the interoperability solutions that can help you communicate or transfer messages between multiple layer ones. So between Ethereum and Bitcoin, you can transmit messages using a layer 0 blockchain. Or for example, as we previously stated, for Polkadot, it is a relay chain that connects many parachains. So all those parachains that exist in Polkadot are considered layer ones. But the relay chains is considered as a layer 0, since it allows for communication between those layer ones. So the layer 0 protocols or blockchains are meant to be for extended communication between multiple layer ones. When it comes to the layer 2, this concept is just like, for example, let's say an example of a layer 2 solution such as Polygon. So Polygon is a famous blockchain network, and it is a layer 2 solution. Why it is layer 2 solution? Because it is under the hood, relying on Ethereum, which is a layer 1 protocol for its security. And there are a lot of mechanisms to go there. There is side chains. So for example, for Polygon proof of stake, they have their own validators, and they submit the proofs in the blockchain Ethereum. So for ZK rollups, there is also another many blockchains that are ZK rollups. So basically, they validate a lot of transactions in one time, and they get a zero knowledge proof, which basically can be considered just as a proof that those transactions were executed correctly off chain. They submit those transactions into a layer 1. So it is basically, when it comes to layer 2, it is an application that is built, or a blockchain network that is built on top of another layer 1 blockchain. So for ZK rollups, as I said, they submit the zero knowledge proof in the layer 1 solution. So they are relying on Ethereum as a main consensus point, and they have their own state in this blockchain. And also there are a lot of layer 2 blockchains that are built into Ethereum, and of course in other blockchains. And there are also, you can even go to layer 3, which, for example, you can build on over a layer 2. And for example, if layer 2 provides scaling, you can include a layer 3 that addresses the privacy problem. So it can address privacy using zero knowledge proofs. There are a lot of research about that. So you can even go to execute transactions in layer 3. For now, there isn't any layer 3 that is famous, but there is a lot of research around that. I don't know if that answers your questions. Feel free to let me know if you have any question.
Yeah, it does. Thank you.
Okay, perfect. Any other questions before moving on to the last roadmap? Okay, so the last roadmap is how to be a smart contract auditor, and more specifically, how to be an Ethereum smart contract auditor. So the ecosystem differ. If you want to audit a contract in Polkadot, which is mainly using Substrate to as its own mechanism. For example, Solana, it's using Rust as a programming language. So the ecosystem, some ecosystems differ. But if you are an Ethereum smart contract auditor, you can audit smart contracts in Ethereum, Binance Smart Chain, Polygon, and all the blockchains that use the EVM, which is the Ethereum Virtual Machine, as their own execution layer. So the first step, which will be just like the being a blockchain developer, you should master how Ethereum works, proof of stake versus proof of work, what are the main differences. You should learn about Solidity, how it works. There are a lot of resources out there, gas optimizations, how you can develop the code in order to optimize gas. Smart contract testing and debugging, you should learn about Foundry and Hardhat, which are the main ones. And Tenderly is a solution for like monitoring and seeing how transactions are executed, etc. Step 5 includes the token standards, which are some standards that are known in Ethereum, such as ERC20 for building fungible tokens, ERC721, which is used for NFTs, 777, which is an extension of the ERC20, just includes some additional functionalities, and other standards like that. So there are some common knowledge that you should know about specifically for the token standards. Step 6 is learning about the OpenZeppelin library, helper library, and contracts. So there are a lot of contracts that are standards that are developed by experts, which are used in almost every contract. So you should know how this works in order for you to audit and understand code. So your main tasks as an auditor, first to understand the code, understand the business logic behind it, what they are trying to do. Then you can find smart contract bugs. So you cannot find any bugs if you do not understand what's the main objective of the smart contract. So you should learn about upgradable contracts. So as we said, smart contracts are immutable by default, but there are some mechanisms such as the proxy pattern, etc., which can help us overcome this by using some proxy contract behind an implementation contract, so we can customize the logic. So you should definitely learn about upgradable smart contracts. That was step 7. Now step 8 is studying smart contract and Solidity attack vectors. As we said, reentrancy, signature replays, rounding errors, overflows, etc. So you should learn all about almost all the most known vulnerabilities that exist out there, and there are a lot of resources to see. Step 9 is to play in CTFs. So capture the flag allows for an environment that is very good to apply your knowledge. So there is Ethernaut, capture the Ether, the vulnerable GFI. Those are provide you with challenges that you can literally hack some contracts in a white hat approach, of course. So you are allowed to do that. This environment is built for you to exploit these vulnerabilities for learning purposes. So the step 10 is to dive into the GFI, which is the decentralized finance. So you should have, there are a lot of resources out there. You should know how finance works from a high level. You don't need to be the most expert in finance in the world in order to be a smart contract auditor, but you learn with time. You learn about the famous protocols that are used almost everywhere in smart contracts, which are Uniswap, Compound, Curve, Aave, Balancer, etc. You should know about how stable coins work, like USDC, USGC. DAI, for example, as a decentralized stablecoin, each coin has its own functionalities, ups and downs. You should learn about the attack vectors that are related to GFI. So there are the attack vectors that focus on the code and Solidity, and there are attack vectors that addresses GFI for GFI as a concept. So those are like financial attacks, which, for example, can be flash loan to manipulate the prices, front running, and sandwich attacks, which we talked about later, etc. And you should also lead the post-mortem and the bug fixes that were introduced before. So if a specific contract is hacked, mainly the project team produced what we call a post-mortem, which is basically they are explaining how the hack happened to the smart contract and what was the vulnerability that was exploited. Those will help you into learning more about the new security vulnerabilities. So if you now learn the security vulnerabilities that are existing, that's not totally enough. You should always, the space is always evolving. You should always keep up with the news and what's happening. So that was step 12. Let's move on to the step 13, which is reading a lot of reports which are produced by auditing companies. So there are a lot of auditing companies such as ourselves, Shellboxes, and other ones. You should read the reports just to know how other auditors think and to learn from them and how they are doing it. The step 14 is to have there are some issues that you should constantly check for. So you can build a checklist that you can use, but you should not only rely on that checklist. So you should just structure your process. So step 15 require just learning more tools. So you should know how to use Slider, Material, and all the tools that as much as you can of the tools that you can use in your auditing process. The step 16, which is the last one, is continuous learning and research. So if you reach this step, then all what's left for you is to get more advanced, read the Ethereum yellow paper, which is mathematically heavy. Read the EIPs that we talked about before. You can explore the research that's being done in Ethereum. Join the communities that are existing in Discord, Telegram, etc. So you should always be active in the community, and that will help you to learn continuously. So that was it for the smart contract auditor roadmap. I don't know if you have any questions concerning that. So yeah, that was it for the presentation, guys. I thank you for your attention. Feel free to let me know if you have any questions. You can also reach out to me in LinkedIn, for example, if you need any information either about the presentation itself or any resources for you to learn or any guidance that you need in order to get in the space. So the blockchain space is a very good one, and it's really promising. A lot of opportunities are there, and yeah, that's it, I guess. So I will leave you like some 1 minute or two in order for you to think if you have any questions before we can ramp up the presentation.
All right, it seems like they have no questions regarding curriculum, so I'll go ahead. All right, thank you for this session. It was really insightful. I'm sure a number of us learned one or two. All right, go on.
I didn't hear what was said. Can you please repeat?
I think someone has a question. Please go ahead.
Yeah, I have a question. So blockchain is using a peer-to-peer network, which means like we are avoiding the DDoS attacks and that single point of failure kind of problem.
Yeah.
So if all the transactions are stored on the network, when someone makes a mistake to send some Bitcoin to a wrong address, it is considered like like a mistake which can be like the money can be recovered, you can follow up on it. Why is that? Because if they have if they have records, they could see where the money went. So why is that? Is it avoiding like to make the network centralized or having someone having power over others? I don't understand why the
Can you
person who sends
simply reformulate your question? I didn't kind of get the main point that you're asking about.
yeah. So when a person sends money to the wrong address, it said that the ledger has all the transactions, but that person can follow up on that issue. Is it because the ledger can be like accessed to find the wrong address he sent to, or is it because there's no one who has more power than others on the network?
So in general, if you are sending some funds by mistake, or for example a hack happens, basically the main thing is consensus. So there happens some case where there is what we call some forks. So for example, there is now Bitcoin, and there is what we call Bitcoin Classic. So Bitcoin Classic is just a fork of Bitcoin where the nodes in a specific case didn't agree to find, or like to find the consensus. So basically we have a chain of blocks, and in the next block there is a validator that provided the next block, and there is another validator that validated over the previous block in order to revert that. So we tend to follow the longest chain, which is the chain of Bitcoin now, but now there is another chain which is Bitcoin Classic, and those forks can happen when either the same block or the same miners solve the problem in the same time. This is when it comes to proof of work, and also when there is not much consensus between the nodes in a specific situation. It also happened for Ethereum before a hack happened, and some nodes decided to literally revert to the previous block in order to revert the hack, and some other ones valued the fact that anything that is executed in the blockchain should stay the same. So the value of immutability and decentralization is broken if we revert back and we change things. So there are, and this is the main chain now. The main chain now is of Ethereum is the one where the hack actually happened, and there is the other chain where they reverted back the hacks. It is called, I assume, Ethereum Classic. For Bitcoin, it is called Bitcoin Cash, not Bitcoin Classic. So there are cases where changes try to revert. So if I send, for example, my funds to the address 0, no one can recover this for me. So the whole consensus, I signed this transaction, and everyone verified that I signed this transaction. So those changes by consensus cannot be reverted. I don't know if I answered your question. Feel free to let me know if you have any other aspects.
Yeah, you did answer the question. And the last question I have is about data, how data is stored. So normally we have databases on a central server somewhere.
Yeah.
And there's maybe a system administrator protecting the database and a few infrastructure. On the blockchain, having different nodes, how is data stored? How is what's considered critical data separated from other data? So if maybe I have a username and I have a password, those are two different data to carry in a different way. So how is data stored on a blockchain to keep this security?
Yeah, so when it comes to that, the data is stored anywhere. So the data basically is replicated over all the nodes. So we do not have a single point of failure. Everyone has all the data. When it comes to what we call critical data, that's another subject. So for Bitcoin, Ethereum, at least the layer ones, everything is transparent. So password should not, on any critical data that should not be visible, should not be stored in the blockchain. Even if you, as I said before, even if you specify a variable in a smart contract as private, you just basically don't get an accessor to it, but the data is actually there and can be accessed by anyone. So private data or data that's sensitive should not be stored in the blockchain, at least in the transparent ones. So transparency is an advantage of the blockchain, but it can also be a drawback. So too much transparency hits the privacy aspect. So if I want to, for example, to send a transaction to someone, everyone can see that I sent this transaction to someone. So there is no privacy here. That's why there is a lot of research when it comes to privacy, and there exist some solutions either in layer 2s or layer 1s that try to address this issue of privacy. There is what we call Zcash, which uses zero knowledge proofs in order to validate transactions. So if the miner validates the transactions, he validates the transactions and produces a zero knowledge proof, which verifies the correctness of the transaction, but without providing us with any data about who sent the funds, to who is the receiver, and how much was sent. So Zcash, for example, there is Tornado Cash, which can help you send Ethereum in the layer 1 in a private way. So it uses ZK snarks as an underlying cryptography technology to address privacy. So in order for you to interact with private data, you need either to use private blockchains, or you need to use some additional cryptographic schemes in order to have privacy, such as zero knowledge proofs. So for example, if we try to store data in Ethereum, you should never store critical or sensitive data that should not be exposed, because anyone can see it, unless you are using a cryptographic scheme that prevents people from doing so.
Yeah, thank you. So maybe that's why if you lose a passphrase to your wallet, that's why you can never recover it.
If you lose your passphrase to the wallet, basically you are indirectly losing your private key. So if someone has the private key, he can execute operations on your behalf. So if you lose your private key, I can literally use your wallet to execute or to transfer your money to my own wallet, or to transfer it to a specific exchange, etc. So that's why if you lose the seed phrase of your wallet, if anyone receives it, anyone can access your wallet and perform operations on your behalf. And there is a lot of research going on into that area too. So for now, there is what we call account abstraction. There is an Ethereum improvement proposal concerning that, which we try to have some sort of social recovery. If you use your private key, you can change it and have the same account. This is using smart account and some advanced technologies behind the scene.
Yeah, that was it. Thank you so much.
Yeah, perfect. So I guess that was it for me. If you don't have any questions, if you have any further questions, reach out to me in LinkedIn. And yeah, I hope the talk was instructive. I hope you liked it, and I hope people have learned new things in this talk. And I want to thank all the audience for their presence, and the Africa Blockchain Institute for the opportunity. Thank you, guys.
Thank you.
Okay, thank you so much for honoring our invitation and taking this workshop here. So I'm sure I know what was learned a thing or two from this session. Either learning is afresh or refreshing on existing knowledge. So I want to ask anyone that has any questions regarding the hackathon, anything like related to the hackathon coming up, please let me know now. Questions.
I have the question.
Okay.
How long will it take? How long is it planned to take?
Will what take the hackathon?
Yes. How long is it expected to take?
It will take 4 hours.
4?
4 hours.
It will be on the spot?
Yes, it's going to be on the spot. It's on the 2nd of August. I think that's Wednesday. at KCC from 9 a.m. to 1 p.m.
Okay.
So the hackathon program starts 9 a.m. to 1 p.m. But everybody should be there by 8 a.m. so as to do registrations and all necessary things.
Oh yeah, so I have a question too about that. So are we expected to build something, or will it be like CTFs having challenges to solve?
I'm sorry, you said?
For the hackathon, are we expected to build something, or is it like solving challenges like CTFs, that kind of stuff?
Okay, so we would present the challenge to you tomorrow after the session tomorrow. And then you're supposed to work on it and come up with, it's advisable to, build a demo or anything, but it depends on you and your team members, what you're able to come up with. Or, just like present you the challenge and then you work together as a team to come up with a viable solution. And to the best of your abilities, if you can build a product, if you can do a pitch deck, it's up to you to come up with what you feel like your best at that point in time.
Another question, will we have the same, or each group will have theirs?
Everybody has the same challenge you're talking about. If that's it, yes, you're going to have the same challenge.
Okay.
Right, so any other question?
So I have a question. So if it's going to be if you're going to be given a challenge tomorrow, so what are you going to be doing exactly on Wednesday at KCCA? We're supposed to be done with that challenge by, before we come there, or we will be doing like a live coding session there? Thank you.
Okay, so on Wednesday, you're expected to continue working on your challenge based on, where if you are able to complete it before that day, you'll still come and continue working on it. It's not possible for you to be able to build a product or do whatever, and you would keep revising or doing something. So we're just giving you time to get started on this thing, get working on it early so that you'll be able to come up with something solid for the presentation, right? So you start working on it as soon as you can, and you continue working on it till 1 p.m., which is when you have to stop. Have I answered your question?
Yes, you did. Thank you.
Any other question? Okay, I'm going to assume that there's no other question. So thank you so much for joining this session. We would share the recording with you via Discord to ensure that everybody is, if you want to go through it again, if you want to listen again, you can do it. And yes, have a good day. We'll meet again tomorrow at the same time for the second part of the workshop. All right, bye.